All right, people. I believe everybody is doing great, nice, and absolutely fine. So, welcome to Unacademy Neet English. Guys, let me know in the chats if I'm perfectly audible, visible to each and every single student, okay? And let the people join. Let everybody come, and we are starting this particular session over here. And make sure everybody of you, okay, smash the like button out there, because liking the session means marking the attendance, and that's extremely mandatory. I would want everybody to smash the like button out there. Good evening, good evening, good evening, good evening. I am doing absolutely great. What about you guys? Okay. Since we have got only 15 days left for the NEET 2025, and I know at this point of time you guys are extremely worried. Okay. This is completely normal. If you ask those students who have cracked before, they were going through the same situation at this point of time. Okay, so don't have to worry about anything. Just keep giving your best. Okay, okay. So be consistent for the next 15 days. Focus on the revisions and the mock test. I have told you the strategy in the morning itself, so that you must start from tomorrow. Okay. So guys, quickly smash the like button now out there. And today we will be completing, we say, a lot of chapters out there when it comes to the physics. Okay. So this will be the complete physics marathon. And my dear friends, listen to me very carefully. I will be starting from the scratch. I will be starting from the scratch. If you have not studied anything before related to these chapters, you don't have to worry about anything. Okay. I will be taking everything from the scratch, and I'll give you, we say, the sufficient content which you actually need in order to solve all the problems out there. Okay. Yes. So guys, okay, make sure everybody of you has smashed the like button. Everyone means everyone. Okay. So I think we need to start. The sequence of the chapters will be starting from the modern physics. Because when it comes to the modern physics, we are expecting 9 to 12 questions. That means 48 marks from the modern physics itself. Extremely high weightage chapters. Modern physics basically consists of 3 to 4 chapters. Okay, we'll be completing first those 3 to 4 chapters. Then we will move on to the semiconductors. Then we'll see the rest of the sequence. Okay? Is that cool? Yes. That's great. Now guys, I think now it is time to start. So guys, I will be starting from modern physics portion. Okay. I will be starting from modern physics portion. First, we will go with the dual nature of matter and radiations. Okay. Like when it comes to the modern physics, you have got 3 to 4 chapters. Dual nature of matter and radiations. You have got atoms, you have got nuclei. Okay. And then we will move on to the semiconductors. And my dear friends, we can say, over here 9 to 12 questions you can expect from modern physics. 9 to 12 questions. Okay. 9 to 12 questions. And my dear friends, 9 to 12 questions means 48 marks. If I say 12 into 4, that is 48 marks. So I would want you guys to give me 100% of your attention, okay, in this particular session over here. Is that clear? Yes. That's great. Now guys, first and the foremost thing when it comes to dual nature of matter and radiations, listen to me very carefully. Guys, whenever we talk about the modern physics, always remember, I'll tell you one thing. What is that? In this particular chapter, we consider light as a particle. Simply remember, here I say in this particular chapter, we say here we consider light as a particle. Okay, means if I say, everybody of you listen to me very carefully, if I say this is a light source over here, if I say this is a light source over here, so light is coming out of this light source, so you'll be assuming that these are the particles coming out of the light source. Keep this thing in your mind. When we'll move on to the wave optics, over there we'll consider this light as a wave. But here we'll consider these as photons. These are the photons coming out of this light source. Okay. And if I say light is falling on my hand, means these are the photons falling on my hand. So these photons have energy. Why? Because light has energy, so these photons have energy. So this is the first statement that I'm telling you over here. When it comes to this dual nature of matter and radiations, we will consider light as particles called photons. These photons will have energy. Okay. First topic that we need to understand in this particular case, that is energy of a photon. Energy of a photon. Guys, see, whenever we talk about energy of a photon, always remember, we say energy of a photon is H into F. H is Planck's constant, F is frequency. H is Planck's constant, F is frequency. Okay. 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 Yes. Okay. Yes. Now, my dear friends, we say when Planck's constant is multiplied with frequency, it gives us the energy of photon. That's it. Now, if somebody asks you, what is the further value of C? We say this frequency is basically C divided by lambda. So we'll put it over here. Instead of frequency, I'll put C divided by lambda. So this is also the energy of photon. Okay. Yes. Then my dear friends, we say, sir, is this also the energy of a photon? Yes, there are different formulas for the energy of photon. I'll not derive these directly. Energy of a photon is simply 2 into 10 raised power minus 25 divided by lambda into joules. Basically, when you put the value of Planck's constant, okay, 6.6 in 10 raised power minus 34 joules second. This is speed of light. So C is 3 into 10 raised power 8. When you multiply those two, you'll get 2 into 10 raised power 25 divided by lambda, and this is in joules. My dear friends, I would want you guys to remember over here, that is one thing. This is the energy of a photon in joules. And here, this lambda is the wavelength, and this lambda is in meters. So you have to use this formula. When we say lambda is given in meters and you have to find the energy in joules. That's it. Okay. Then, my dear friends, do we have further more formulas when it comes to the energy of photon? Yes. Sir, this is also the formula of energy of a photon. 12400. But here lambda is in nanometer. Okay. And this is in electron volt. Energy is in electron volt. Means this is the energy of a photon in electron volts. Like this is we can find the energy in joules also. We can find the energy in electron volts also. So basically we use this formula when lambda is given in nanometer. Sir, this is also the energy of a photon. Yes. This is also the energy of a photon in electron volt when lambda is given as angstrom. Now guys, listen to me very carefully. I'll make you understand this particular thing over here. Let's suppose everybody of you listen to me very carefully. Let's suppose light is falling, means photon is falling. Okay. And I'm saying this photon has got the wavelength of 310 nanometers. Okay. You guys are supposed to find the energy of a photon in electron volts. You have to find the energy of a photon in electron volts. Okay. Now here, I'm saying there is another photon. This photon has got the wavelength, let's suppose 4000, I would say, angstrom. And you guys are supposed to tell me energy of a photon in electron volts. Listen to me very carefully. Listen to me very carefully. Guys, we say when lambda is given in nanometers, energy you guys are supposed to find in electron volts, you'll be using this formula. You'll be using this formula. So directly you will be saying over here, energy of a photon is 1240 divided by lambda, and it is in nanometers. This energy is in electron volts. So we'll be writing 1240 divided by, instead of lambda, you'll be putting 310, and this will give you the energy of a photon in. This will give you the energy of a photon in, we say, electron volts. And here, you'll be using the energy of a photon. Listen to me very carefully. You'll be using the energy of a photon as, that is 12400 divided by lambda, and this lambda is in angstrom. This energy will be in the electron volts. So here it will be 12400 divided by 4000, that will be 3.1. So this will give you the energy of a photon in electron volts. Exactly. So my dear friends, I hope you got the crystal clear feel of these formulas. If you want to find the energy of a photon in electron volt, de Broglie's wavelength is given in nanometers, you use this formula. When you have to find, when lambda is given in angstrom, so you'll be using this formula. And if you have to find the energy in joules, you'll be using this particular formula. Keep that thing in your mind. Like you have the first question on the screen, I would want you guys to tell me the answer of this particular question. Everybody of you. Let me know what is going to be the answer for this particular question. Everyone means everyone. See guys, I'm saying, what is the energy in joule associated with a photon of wavelength this? It says that you have got a photon over here which has got the wavelength of 4000 angstrom. You have got a photon which has got the wavelength of 4000 angstrom. You have to find the energy in joules, and you have to find the energy in electron volts. Both. Guys, see, when you have to find the energy in joules, which formula you guys are supposed to use? 2 into 10 raised power minus 25 joule divided by lambda. This is in meters. So this is a formula which you need to use when you have to find the energy in joules. And my dear friends, this is the formula which you need to use. 12400 divided by lambda, that is the angstrom in electron volts. This is the formula which you need to use when you have to find the energy in electron volts, and lambda is given in angstrom. So here you'll be writing 2 into 10 raised power minus 25 divided by lambda is given as, we say, 4000 into 4000 into. So this will be 10 raised power minus 10. Why? Because if you have to convert angstrom into meters, you have to multiply with 10 raised power minus 10. Okay. Now here, you'll be simply saying, sir, 12400 divided by, this will be in this particular case, that is 4000 directly. Okay. So this will come out to be 3.1. This will come out to be, we say, 0.18 into something. Okay. Do check it from your end. I hope you got the feel of this particular question. Crystal clear feel. Okay. I hope you got the proper feel of this particular question. Okay. Yes. 5 into 10 raised power minus 19. That's great. Okay. This is 3.1. So basically, when you have to find the energy in joules, use this formula. When you have to find the energy in electron volts, you have to use this particular formula. Okay. Yes. Is this clear? Please let me know in the chats with the fire emojis if all the formulas of energy of photon is clear. Let me know in the chats with the fire emojis if all the formulas are crystal and clear. And smash the like button, guys, okay? And don't forget to join my Telegram channel, okay? Where I share all the updates, notes, everything. That is t.me/YAWAR MANZOOR. Okay, don't forget to join this Telegram channel where I share all the updates, every single thing. Okay, guys. Okay. And after this particular series, I'll be coming up with the sure shot concepts along with the problems, which has the highest probability that these questions only will be asked in your NEET exam after this. Okay, so be ready for that also, like the last year, Okay. Now guys, take a look. Let's talk about energy of light. I would want you guys to focus exactly over here. Energy of light means, see guys, energy of light means, we say, when it comes to, let's suppose this is a light source over here. So these are the photons coming out of light source. Yes, these are the photons coming out of light source. What is the energy of one photon? That is H into F. Or you say Hc divided by lambda. Now, how many number of photons are there? It is not one photon. There are n number of photons. So we say energy of n photons, it will be NHF, or you say NHc divided by lambda. So this itself, this energy of n photons means energy of light. So this will be energy of light because n photons form the light. So directly I can say in this particular case, energy of light is NHc divided by lambda. Okay. Where n is the number of photons? Okay. Now guys, power of light. We say power is defined as energy per second, total energy per second, or total energy radiation per second. See guys, let's suppose this is a light source over here. Okay, let's suppose this is a light source over here. Light is coming out of the light source, it is falling on my hand. Every second, how much light is coming out? How much energy is coming out? Okay. Every second, how much energy is coming out? Every second, how many number of photons are coming out? That is what we call the power. If I say this is a strong bulb, every second, a lot of light is coming out, a lot of photons are coming out. So we say power is large. Sir, this is not a good bulb. Every second, less number of photons are coming out, less light is coming out. So we say power is less. So how do we define power? Energy upon time, energy per second. What is the energy of light? NHc by lambda. That is NHc divided by lambda divided by time. So this will be the power of light. NHc divided by lambda into T. Okay. Now guys, there is a question over here. The question is, let Nr and Nb be respectively the number of photons emitted by red bulb. You have got a red bulb over here. Take a look. Let's suppose you have a bulb over here. This is a red bulb. Okay. And light is coming out of this red bulb. And you have a blue bulb over here. Okay. Now in this particular case, it says that number of photons emitted by the red bulb and the blue bulb. Okay, Nr and Nb. Okay, number of photons coming out of this is Nr. Number of photons coming out of this is Nb. Okay, and each bulb has got the equal power. We say power of red is given as power of blue. Power of red in this particular case is given as power of blue. And you guys are supposed to tell me in this case, that which one will emit more number of photons. Take a look. Guys. What is the value? How do we write power? Power means NHF divided by time. Okay, NHF, that is number of photons, Planck's constant, F is frequency divided by time. This is energy upon time will be equal to power of this, NHF divided by time. Guys, see. Here, number of photons of red, frequency of red. Number of photons of red, blue, frequency of blue. And H, Planck's constant is same. H and H will cancel, this and this will cancel. So can I say number of photons of red, frequency of red is equal to number of photons of blue will be frequency of blue. Now guys, always remember, when it comes to the frequency of red, we say frequency of red is less than frequency of blue. Directly remember this. Guys. In this case, we say multiple of these two are equal. Number of photons of red and number of photons of frequency of red. Multiple of these two is equal to these two. Now, if I say one quantity is lesser over here and this quantity is large, means this quantity must be large, this quantity must be small here, then only their product will be equal. So can I say in this particular case, number of photons of red are greater than number of photons of blue? Number of photons of red are greater than number of photons of blue. Is this clear, guys? Is this clear? So we say red will emit more number of photons. Red will emit more number of photons. Then we define intensity. Guys, take a look. How do we define intensity? Intensity means energy per second per unit area. Means power upon area. Guys, see. If I say this is the light is coming, if I say this is the bulb, light is coming out of this light source, okay, bulb. Now, how much energy is coming out every second? That is energy. Now, if I say, guys, take a look. I'll give you the example. Let's suppose this is the area over here. This is the area over here. Okay. And this is the bulb. This is the bulb. We say photons are coming out of this bulb. Photons are coming out of this bulb and it is falling on this. Photons are coming out of this bulb and it is falling on this. It is falling on this. Okay. Now, if I say every second, how many number of photons are falling on this? Every second, how many number of photons are falling on this? Okay. Every second, how many number of photons are falling on the unit area? We say here, more number of photons are falling on the unit area, per unit area, means intensity is large. Intensity is large. Intensity is defined as energy per unit time, per unit area. How many number of photons are falling every second on this unit area? If more number of photons are falling on this unit area every second, intensity is large. How do we define intensity? Power per unit area. Power is NHC by lambda into T. This much is power divided by area. That's it. So this will be the intensity. Or you can say instead of C by lambda, you can write F only. So I is equal to NHF divided by A into T. Number of photons, Planck's constant, frequency, area, time. I hope this is crystal clear to each and every single student. Okay. Then guys, let's move on to the photoelectric effect. Okay, let's move on to the photoelectric effect. Before that, let me tell me in the chats quickly. Is this crystalline clear? Everyone means everyone. That's great. Now guys, let's move on to the photoelectric effect. See, what does photoelectric effect actually mean? Are 19 H into C, sir, it is coming out to be 19.8. We are approximately saying 2 into 10 raised power minus 25. Now guys, take a look. In this particular case, photoelectric effect. What does photoelectric effect mean? Photoelectric effect means when light falls on a photosensitive metallic surface. Let's suppose this is a metallic surface, a metal surface. This is the light source. Light is falling from this light source and it falls on this metal surface. And we saw that electrons are ejected from the surface. We saw that electrons come out of this surface. So this process is called photoelectric effect. Photoelectric effect means nothing but falling of photons, falling of light on a metal surface, photosensitive metal surface, and coming out of the electrons. Okay, that is called photoelectric effect. Like this is a light source. These are the photons falling on this metal surface. We say electrons are ejected. This phenomena, this process called photoelectric effect. Now here we define a term that is called work function. Work function, we represent with it phi. So we say it is the minimum energy required. It is the minimum energy required to pull the electrons from a material is called a work function. What does that actually mean? Let me just give you the example over here. See guys, let's suppose this is a metal surface, okay? Let's suppose if I say its work function is 2 electron volt. What does it mean? It means if you have to pull out the electron from this metal surface, you will have to send a photon. You will have to send a photon. That photon must have the energy minimum at least 2 electron volts. Then only it can take out the electron from this metal surface. If its energy is, let's suppose, 1 electron volt, it cannot take out the electron. Why? Because work function is 2. Work function tells you how much is the minimum energy required in order to pull out the electron from the metal surface. Okay. How much is the minimum energy required in order to pull the electrons from the metal surface? Like here, we say 2 electron volts. Here, it is 2 electron volts. It is 2 electron volts required. Okay. Like this metal surface, here it is 5 electron volt. Means if you have to pull out the electron from this metal surface, how much energy is required? 5 electron volt. If you send a photon which has a energy of 4 electron volts, it cannot take out. Why? Because minimum energy required is 5. So it depends upon the metal. Some metals will be having the less work function. Some will be having the more work function. Now take a look. Experimental setup of photoelectric effect. Experimental setup of photoelectric effect. Experimental setup of photoelectric effect. Guys, take a look. So how do we exactly perform this photoelectric effect? What is the proper setup in which we perform this photoelectric effect? See guys, you have got a vacuum chamber over here. This is the vacuum chamber. Okay. And in this vacuum chamber, you have got an opening over here. This is the opening. Okay. And my dear friends, here, you place a metal surface which is called cathode. Here it is anode. Okay, here it is anode. This is a metal surface. And you place a light source over here. So these are the photons coming out of the light source. These are the photons coming out of the light source. Okay, and these are falling on this cathode or metal surface. Then here we say voltmeter is connected in order to measure the potential difference. Ammeter is connected and we say a battery is connected over here. This is the switch. This is the entire setup. Now guys, I want to make you understand one particular thing. Lag. Is it lagging? I don't think so. Yeah. No, it's not lagging, bro. Now guys, take a look. So basically, when these photons fall on this metal surface, what will happen? Electrons come out. These are the electrons which are coming out of the metal surface. Now guys, listen to me very carefully. If I say work function of this metal surface is 2 electron volt. Listen to me very carefully. If you want to pull out the electron from this metal surface, you have to send the photons. This has some work function. We say, let's suppose work function is 2 electron volt. You are sending a photon of, let's suppose, 8 electron volt. Okay. Guys, understand one thing very carefully. In this case, we say, let's suppose this is the cathode. Okay. And you are sending a photon over here, which has the energy of 8 electron volt. Here work function is 2 electron volt. So basically, will the electron come out? Yes. Why? Because work function is only 2 electron volt. So electron will come out. So now 8 electron volt, 2 electron volt is using in coming out of the metal surface. What about rest of the 6? 8 minus 2 is 6. So rest of the 2 it is using in the kinetic energy. That is rest of the 6 electron volt it is using in the kinetic energy. So can I say in this particular case, guys, take a look. Can I say in this particular case, energy of a photon is basically used in work function. Means to pull out the electron from the metal surface. And rest of the energy goes into the kinetic energy. So it will be something like this. So energy of a photon plus work function plus kinetic energy, and I would say this is kinetic energy maximum. We say kinetic energy maximum. Okay. Okay. And this is called Einstein's photoelectric equation. This is called Einstein's photoelectric equation. Okay. This is called Einstein's photoelectric equation. That is, energy of a photon is equal to work function plus kinetic energy maximum. This is called Einstein's photoelectric equation. Okay. Yes. Now, what does it further say? Further, if we talk about over here, if 10 electrons are coming out of cathode and 4 are only reaching anode. Now, see. Okay. Let me just make you understand this graph over here. See, guys. Let's suppose here, what I'm trying to say is that, this is the cathode. Just a second, guys. Let's suppose this is the cathode. This is the cathode. Okay. Now, if I say these are the electrons, 10 electrons are coming out of the cathode. Okay. Okay. These are the 10 electrons which are coming out of the cathode. These are the 10 electrons which are coming out of the cathode. Okay. These are the 10 electrons which are coming out of cathode. And only 1, 2, 3, 4. Only 4 are able to reach anode. Only this is anode. Only 4 are able to reach anode. Now, my dear friends, I want you guys to understand one thing. What do we do in this particular case? We say. In this particular case, we say only 4 are able to reach anode. What we do is we connect a battery. Okay. We connect a battery. And when we connect a battery, we connect positive terminal from this side, negative terminal from this side. So this positive terminal basically occupies positive charge on the anode. Let's suppose we are applying few volts of potential difference. Okay. See guys. What I'm trying to say is that we say when there was no battery means zero EMF. At that point of time, 4 electrons were reaching anode. Now, when you are applying the battery potential difference, 10 volt, 20 volt, let's suppose at 10 volts, how many electrons? Now, some positive charge is occupied. It will attract one more electron. Now, 5 electrons are reaching. Now, when you apply 20 volt, we say 6 electrons are reaching. Now, you are increasing the voltage. So, positive charge is increasing. It is attracting the electrons. When you are applying 30 volts, we say 7 electrons reaching. When you are applying 40 volts, we say 8 electrons reaching. When you are applying 50 volts, we say 9 electrons reaching. When you are applying 60 volts, we say 10 electrons reaching. When you are applying 70 volts, we say now how many? We say still 10 electrons are reaching anode. Why? Because only 10 electrons are there. Only 10 electrons have come out. So now guys, this flow of electrons, what does it mean? This forms current that is known as photocurrent. Because whenever electrons flow, we say current is being produced, and this current is what we call the photocurrent. Now see, this is EMF versus photocurrent. If we make the graph, photocurrent versus EMF. Guys, when EMF was 0 volt, how many electrons were there crossing? 4. So current was not 0, current was 4. As we keep on increasing the EMF, 10 volt, 20 volt, 30, 40, 50, 60, 70. Okay, we say current is increasing. When we say, when potential difference reaches 60 volt, current becomes constant. 10 electrons. We say, so in this particular case, when potential difference, when this becomes, we say 60 volts, then current becomes constant. Even if you increase 70, 80, only 10 electrons are there, we say current is then constant. Okay. Yes. Now, one more important thing. So till here, I made you understand what the graph says. Then, my dear friends, in this particular case, in the same thing, in the same setup, just a second, understand this very carefully. I'll add the slide over here. Yes. Guys, take a look. What I'm trying to say is that, listen to me very carefully. If we reverse the polarity of the battery, reversing the polarity means this is now the positive terminal, this is the negative terminal. This is the positive terminal, this is the negative terminal. So reversing the polarity means you are basically, just a second, let me erase these. Reversing the polarity means you are increasing the negative potential. You are increasing the negative charge over here. Okay. Let's suppose at 0 EMF, how many electrons were flowing? 4. When you apply, let's suppose minus 10 volts, okay, means some negative charge. Now it is repelling the electrons. Negative charge repels the electrons. Okay. So I say in this particular case, only 3 electrons will reach. Why? Because now electrons are facing repulsion. When you apply minus 20 volts, now only 2 electrons are reaching. When you apply minus 30 volts, only 1 electron is reaching. When you apply minus 40 volts, now all the electrons are facing maximum repulsion. We say 0 electrons are reaching. Can I say at this point, photocurrent is 0? No photocurrent flows? Yes. Now take a look at the graph. See guys, if you keep on increasing the negative potential, minus 10 volts, minus 20 volts, minus 30 volts, and here minus 40 volts, means current will keep on decreasing. 4 electrons at 0 volt. Now 3, 2, 1, 0. So this voltage, this potential at which no current flows is called stopping potential. This potential at which no current flows is called stopping potential. Okay, stopping potential is that negative value of potential at which no current flows. So this is what we call stopping potential. So this is the complete detail about photoelectric effect, and there is nothing much in this one. I have made you understand the graph also and this also. Okay, yes. And one more important thing I just want to say over here. See, take a look. Guys, when it comes to the Einstein's photoelectric equation, this is work function plus kinetic energy maximum. You can write it like this also. You can say this energy of photon, it is h into f. And here you can say this will be h into f naught. This is the minimum energy. Phi is the minimum energy at which photoelectric effect takes place. F naught is the minimum frequency at which photoelectric effect takes place. And then we say kinetic energy maximum. You can write, we say guys, you can write it like this also. You can write it 1/2 mv square also. You can write this Einstein's photoelectric equation something like this also. Keep this thing in your mind. And one more important point I just want to say, that is always remember, at stopping potential, we say kinetic energy maximum will be equals to EV naught. At stopping potential, kinetic energy maximum will be equals to EV naught. V naught is the stopping potential. E is the charge on an electron. Okay, EV naught. Is this clear? Is this clear? Please tell me in the chats, guys. Is the photoelectric effect clear to each and every single student? Let me know quickly in the chats. Tell me. Now, guys, take a look. Some of the questions related to photoelectric effect. Take a look. Take a look, guys. For a certain metal, this nu, consider this as frequency F. F is 5 times F naught. F naught is the threshold frequency. It is that frequency at which photoelectric effect takes place. The maximum velocity of the photoelectron is this. See, guys. See, guys. This is a metal surface. This is a metal surface, I'm saying. Okay. A photon is falling on this. A photon is falling on this. And frequency of this photon is simply 5 times the threshold frequency. Frequency of this photon is simply 5 times the threshold frequency. Okay. And due to this, an electron is coming out. Due to this, an electron is coming out. Due to this, an electron is coming out. Okay. And this electron, due to this, an electron is coming. This electron has a velocity V1 is equal to 8 into 10 raised power 6. Okay. Yes. If frequency F is equal to 2 times of F naught, F is equal to 2 times of F naught. Now, let's suppose another photon is falling on this one. Another photon is falling on this one, which has got the frequency F is equal to 2 times of F naught. Due to this, another electron will be coming out. This will have the velocity V2. That is what we need to calculate. The maximum velocity of this photoelectron will be. Okay, this is the first part of the question. This is the second part. Guys, see. In case 1, if we use the Einstein's photoelectric equation, what does that say? Energy of photon is equal to work function plus kinetic energy maximum. Energy of photon is equal to work function plus kinetic energy maximum. Energy of photon, how much that will be? H into F. This will be H into F naught plus 1 by 2 mv square, V1 square, because we are talking about this electron. H into F. What is the frequency of this? 5 times F naught. So H into 5 times F naught. I'll write it like this. H into 5 times F naught. And this will be H F naught plus 1 by 2 m V1 square. Okay. Now, guys, 5 times HF naught minus HF naught. This will come out to be 4 times HF naught is equal to 1 by 2 mv1 square. You can write it like this. This is the equation first. Okay. Now use the equation in the second case. Okay. Use the equation in second case. Okay. Case 2. In case 2, we can say what is the energy of a photon? That is going to be H into F is equal to okay, is equal to H into F. And we can say here also it is H into F naught plus 1 by 2 mv2 square. But in case 2, what is the value of F? That is 2 times of F naught. So I can write 2 times of HF naught, okay, minus HF naught will be equals to 1 by 2 mv2 square. This is the, now this will be 2 minus 1 is 1. So that is HF naught will come out to be 1 by 2 mv2 square. This is the equation second. This is the equation second. Now, guys, divide first and second. Divide first and second. If we divide first and second, what we are going to get? That will be H4 times HF naught divided by HF naught will be 1 by 2 mv1 square upon 1 by 2 mv2 square. This and this will cancel. HF naught will cancel. So this will be V1 divided by V2 whole square will be equals to 4. So V1 divided by V2 will come out to be root 4, that is 2. We are supposed to find V2. So V2 will come out to be V1 divided by 2. What is the value of V1? 8 into 10 raised power 6. So this will be 8 into 10 raised power 6 divided by 2. That will be 4 into 10 raised power 6 meter per second. 4 into 10 raised power 6 meter per second is the velocity of the second electron. Is the velocity of the second electron. Is this clear, guys? Smash the like button if you have not liked the session yet. Do it quickly, do it quickly. Now, on the similar concept, we have got another question. Take a look. 2 radiation of photon energy is 1 electron volt and 2.5 electron volt. Okay, this is a metal surface and there is a radiation photon falling. It has got the energy that is 1 electron volt. Another radiation is falling. It has got the energy 2.5 electron volt. Okay. And work function of this is 0.5 electron volts. Okay. Work function is 0.5 electron volts. The ratio of maximum speeds of the emitted electrons will be. So when this falls on this one, so electron will be ejected. So it has got the speed V1. When this falls on this one, here it is V2. Here it is V2. Okay. Now guys, take a look. In this particular case, you guys are supposed to tell me the ratio of, we are supposed to find what is the value of V1 divided by V2. Similar concept. See, use the case one. Use Einstein's photoelectric equation. That is energy of photon is equal to work function plus kinetic energy maximum 1 by 2 mv1 square directly. Energy of photon is how much? 1 electron volt. Work function is 0.5 electron volt plus 1 by 2 mv1 square. So 1 minus 0.5, that will be 0.5 only. So I can write 1 by 2 electron volt will be equals to 1 by 2 mv1 square. Call this as equation first. Then guys, I can write over here case 2. When it comes to the case 2, here, what is the energy of a photon? 2.5 electron volt. Okay. So this will be 2.5 electron volt is equal to work function 0.5 electron volt. Okay. Then plus 1 by 2 mv2 square. This is the second equation. 2.5 minus 0.5. This will be 2 electron volt is equal to 1 by 2 mv2 square. Okay. Now call this as second equation. Now divide first and second. Divide first and second. So you'll be writing over here 1 by 2. Okay. 1 by 2 divided by this 2 into this 2. Electron volt will be equals to 1 by 2 mv1 square divided by 1 by 2 mv2 square. Something like this. So 1 by 2 m, 1 by 2 m. This will be 1 by 4. 1 divided by 4 electron volt is equal to V1 divided by V2 whole square. Okay. Now I can say V1 divided by V2 will come out to be equals to that is, see, this will go over here. This will be root of 1 by 4. Okay. Instead of this square, it will be, so this will come out to be 1:2. Ratio is 1:2. Exactly. 1:2. Now guys, one more important fact I just want to say over here. Take a look. Guys, what is the energy of a photon? That is h into f. So energy of a photon is related to frequency. If frequency increases, we say energy of photon increases. Okay. We say if f increases, we say then due to which energy of photon increases. Okay. Yes. Now guys, then we say energy of a photon. Understand this very carefully. Then we say now energy of a photon is equal to work function plus kinetic energy maximum. Now if energy of photon increases, okay, if energy of photon increases, then we say kinetic energy maximum is going to increase. kinetic energy maximum is going to increase. Okay, yes. Now, if now, tell me one thing. Now, we say kinetic energy maximum is E V naught. What is V naught? Stopping potential. Now, if I say, if kinetic energy will increase, we say due to which, we say stopping potential V naught will increase. So basically they are related to each other. That's what I'm trying to say. If frequency increases, energy of photon increases. Okay. If energy of photon increases, kinetic energy maximum increases. If kinetic energy maximum increases, stopping potential increases. That's what I'm saying. On increasing frequency, energy of photon increases. Kinetic energy maximum increases, stopping potential increases. Okay, they are related to each other. They are related to each other. Then take a look. At this series. Very important. Intensity. Guys. We say when it comes to the intensity, it is NHF divided by A into T. This is the formula of intensity. Guys. We say if intensity increases, don't you think due to which number of photons are increasing? So means number of photons increase. Or we say if large number of photons are falling, we say intensity is large. Okay. Yes. Now tell me one thing. We say if more number of photons will fall on a metal surface, chances are there more electrons will be emitting. Yes. Now, if number of photons increase, due to which we say number of electrons increase. And if number of electrons increase, due to which photocurrent will increase. Obviously, if more number of electrons will flow, photocurrent will increase. So they are related to each other. That's what I'm trying to say. Now, guys, what I want to say in this particular case is this one. Frequency and stopping potential are related to each other. Frequency and stopping potential are related to each other. Okay? Directly proportional. Intensity and photocurrent are related to each other. That's what I'm trying to say. Intensity and photocurrent. Yes. Now, take a look at this graph. Photocurrent versus EMF. So this is the graph of different photoelectric effects. Okay. This is the graph. Three graphs. These are the graph of three experiments. Now, can I say in this particular case, guys, here, photocurrent is same. If photocurrent of all these graphs is same, because this is the photocurrent. If photocurrent of all these graphs is same, and photocurrent has a relation with what? Intensity. So can I not say in this particular case, if photocurrent is same, can I not say intensity is going to be same? Yes. Can I not say intensity is going to be same? Now see, stopping potential of this V1 for another graph V2, for another graph V3, we say stopping potential V0 is different. So can I say stopping potential is related to frequency? Frequency is different. That's what I'm trying to say. So this stopping potential is less, more. So frequency of this is more. So F3 is greater than F2 greater than F1. I hope this is crystalline clear. Okay. I hope this is crystalline clear. Take a look. Here, guys. In this case, I can say intensity. I can say here, photocurrent is different. So can I say intensity will be different? Photocurrent is different, intensity is different. And in this particular case, my dear friends, we say stopping potential is same. We say stopping potential is same. So if stopping potential is same, means frequency is same. That's what I'm trying to say. Now, this was the graph which was asked in AIPMT 2014. See. The graph is something like this. I'll make it over here. It is something like this. Okay, this is curve A, this is B, and this is C. Now, can I say, guys, in this particular case, B and C has got the same photocurrent, but B and C has got the different frequency because stopping potential is different. Okay, and A has got different photocurrent, but A and B has got same frequency. See, curve B and C represent incident radiation of different frequencies. B and C has got different frequency. Yes, 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 yes. Stopping potential is different, frequency is different. Of different frequency and different intensities. No, it is wrong. Intensity is same because photocurrent is same. Curve B and C represent the incident radiation of same frequency. Wrong. This is wrong. Curve A and B represent the incident radiation of same intensity. A and B has got the same intensity. This is also wrong. Curve A and B represent the incident. A and B represent the incident radiation of different frequency. A and B has got the different. Why am I making the mistake? See, when it comes to A and B, they have got different intensity, but A and B has the same frequency. Okay. Curve A and B represent the incident radiation of different frequency. A and B has got the different frequency. No, A and B has got the same stopping potential, frequency is same. Curve A and B represent the incident radiation of same frequency. A and B has got the same frequency, yes, but different intensities. Yes, B. Yes. Okay. Now, guys, take a look. Matter wavelength, or we say de Broglie's wavelength. What does it say? What does it say? We say everything in this universe has a wave nature, and a wave is associated with it called matter wave. De Broglie said everything in this universe, okay, be it this pen, be it me, board, everything, okay, has a wave nature. Like when it comes to this pen has the particle nature. This pen has the particle nature. We can feel its particle nature. But when it comes to the wave nature, everything in this universe has a wave nature, and a wave is associated with it. That wave is called matter wave. That wave is called matter wave, or that is called de Broglie's wave. That wave is called de Broglie's wave. Okay. And if I say what is the wavelength of that, that will be lambda is equal to h divided by mv. H is Planck's constant, m is mass, v is the velocity of light. Okay. So, my dear friends, everything in this universe you see has a wave nature associated with. Everything you see is a wave. What is the wavelength of that? H divided by mv. This is according to the de Broglie. Okay. Okay. Or you can say mv is also momentum. P is the momentum. Okay. Yes. Now, guys, if every particle in this universe is a wave, according to the de Broglie, like we say that has got a wave nature. Similarly, in this particular case, if you have different particles. So first of all, when it comes to the de Broglie's wavelength in terms of momentum, so you write it like this: lambda is equal to h divided by mv, or lambda is equal to h divided by p. This is in terms of momentum. If you have to write de Broglie's wavelength in terms of kinetic energy, that would be something like this. H upon under root of 2mke. This is de Broglie's wavelength in terms of kinetic energy. De Broglie's wavelength in terms of kinetic energy. Now guys, de Broglie's wavelength for a relativistic particle, it is that particle which has got extremely huge speed. Speed which is comparable to the speed of light, like electron, proton. For these kinds of particles, this is the de Broglie's wavelength. H lambda is equal to H under root of 1 minus v square by c square. V is the velocity of that particle, speed of that particle, divided by m naught. M naught is the rest mass. V is the velocity of that particle. C is the speed of light. Okay. Yes, yes, yes. Now, if there is a particle which is accelerated with potential difference delta V, it has got the de Broglie's wavelength H upon under root of 2mq delta V. This is the de Broglie's wavelength of that particle. Okay, m is the mass, q is the charge, delta V is the potential difference. Delta V is the potential difference. Okay. Charge at rest in electric field. If you have placed a charge, guys, if you have placed a charge in the external electric field, okay, this is charge q, its mass is m. Its de Broglie's wavelength is h upon qet. H is the Planck's constant, q is the charge, E is the electric field, T is the time. H upon qet. Okay. Now, my dear friends, I want you to understand this. Charged particle placed in a magnetic field. Whenever you place a charged particle in the magnetic field, its de Broglie's wavelength is h upon qbr. H is Planck's constant, q is the charge, b is the magnetic field, r is the radius. Now guys, what kind of radius? Whenever you place a charged particle in the external magnetic field, like this is the inward magnetic field. This is the inward magnetic field. Okay. It will perform a circular motion and it will have the radius r. So this is the charge q. Okay. Okay. Magnetic field is b, charge is q, radius is r, h is Planck's constant. This is the de Broglie's wavelength. Okay. Now for a gaseous molecule at temperature T, it is h upon 3m kBT. Kb is the Boltzmann's constant, T is the temperature. T is the temperature. So for different particles, de Broglie has given the different wavelengths, okay? For an electron moving in the nth orbit of an atom, like guys, this is the nucleus of the atom, okay? And around the nucleus, we say electron is revolving. And this is which orbit? This is nth orbit. So if an electron is revolving in the nth orbit of an hydrogen atom, then its de Broglie's wavelength is NH. N means nth orbit. 2m 13.6. 2m 13.6. Now take a look at this question. This was the question which was asked in Neet 2021. The following will have the same kinetic energy. Which one has the largest de Broglie's wavelength? Which one? Alpha particle, proton, neutron, and electron. So it says you have got different particles. Guys. We say de Broglie's wavelength, understand this very carefully. It says de Broglie's wavelength. Okay. It says following have got the same kinetic energy. Okay. Which one has got the largest wavelength? Guys. When it comes to the mass of alpha particle, we say it is greater than mass of neutron, which is equal to the mass of proton, because mass of proton and neutron we almost consider same, which is greater than mass of electron. What I want you to understand here is, guys, we say when it comes to the de Broglie's wavelength, it is h upon under root of 2m ke, 2m kinetic energy. De Broglie's wavelength is equal to under root of 2m into ke, 2m into ke. So I can say this lambda will be, when it comes to all of these particles, they have got the same kinetic energy. Kinetic energy is same. H is same, 2 is same. So we say lambda is inversely proportional to mass. So means the one which has got large mass will have less de Broglie's wavelength. So we say lambda of alpha particle will be less than lambda of neutron will be equals to the lambda of proton will be less than lambda of electron. Why? Because electron has less mass. So its de Broglie's wavelength is large. So which option? Option D. Option D. Option D. Find the ratio of velocity of proton and alpha particle if the de Broglie's wavelength of both the particles is same. Guys, what does the question say? You have got a proton and alpha particle. Alpha particle. Okay, it says de Broglie's wavelength of alpha particle is equal to de Broglie's wavelength of proton. So how do we write it? Sir, it is h upon mass of alpha particle, velocity of alpha particle, h by mv. And here it is h upon mass of proton, velocity of proton. I want you to understand this. Guys. Can I write this is h upon? Guys, always remember, mass of alpha particle is 4 times mass of proton. Because we say alpha particle is made up of 2 protons, 2 neutrons. So that's why we say 4 times mass of proton. So this will be mass of alpha particle is 4 times mass of proton. Then we say velocity of alpha is equal to h upon mass of proton, velocity of proton. H and H will cancel, MP and MP will cancel. So take it over here. We have to find the ratio of velocity of proton. Okay, Vp divided by V alpha. It is going to be 4:1. It is going to be 4:1. Okay, this question. This was the question asked in NEET 2016 and IIT JEE 2021. Yes, you need to memorize these formulas. You need to memorize these formulas. That is important. Okay. Now guys, take a look. I want you to understand this. An electron and a proton have the same energy E in the range of a few electron volts. Okay. Yes, electron and a photon. The ratio of de Broglie's wavelength associated with electron and wavelength of the photon means we have to find wavelength of electron divided by wavelength of photon. This is what we need to calculate. These are the options. Guys, see, I want you to understand here. When it comes to an electron, we say for an electron. How do we find the de Broglie's wavelength and kinetic energy is given? We say lambda is equal to h upon under root of 2m kinetic energy. Instead of kinetic energy, it is given as E. So this is the de Broglie's wavelength in terms of kinetic energy. Okay? Yes. When it comes to the photon, for a photon, guys, this is de Broglie's wavelength of electron. When it comes to de Broglie's wavelength of photon, it will be h upon we say under root of we say h upon under root of 2mke. Okay, so here when it comes to the photon, guys, we use this formula. Energy of a photon is equal to hc divided by lambda. If you remember, general formula. So you can say over here, lambda of photon, this lambda will come out to be hc divided by E. Now it says both have got the same energy. Now divide the two. We say lambda of electron divided by lambda of photon. It will be. So this is h upon under root of 2m into E upon. So this is hc divided by E. Okay. Now, my dear friends, I can write it like this. Lambda of electron divided by lambda of photon. It will be, that is h upon under root of 2m into E. Okay. Multiplied by, take this in the numerator, E upon, we say h into C. Okay. Now this h and this h will be cancelled. So it is. So take this over here. This is 1 divided by C, and it is E upon under root of 2m into E. It is not matching with the options. Okay, do one thing. Multiply with root E and divide with root E. Guys, root E into root E. Root E into root E becomes E. That will cancel with this E. So what is the final answer? 1 divided by C. Now this is root E upon root 2m. So it will be under root of E divided by 2m. Value of root we write 1 by 2. So it is 1 by C. Then we say E divided by 2m whole raised power 1 by 2. E divided by 2m whole raised power 1 by 2. No, not this one. E divided by 2m whole raised power 1 by 2. Option A. Option A. Okay. Now guys, let's move on to the next chapter, that is atoms. Okay. Let's move on to the next chapter, that is atoms. Let's move on to the next chapter, that is atoms. We are done with all the concepts of de Broglie's wave of photoelectric effect, or what do we call this? Dual nature of matter and radiations. Please tell me in the chats if everything is crystalline clear with the fire emojis. If you have not liked the session, guys, do it quickly as soon as possible. Now guys, take a look. Let's move on to this one. So basically in the atoms, we have to study different models of atom. We have to study different models of atom. The first one will be Thomson's model of atom. The first one will be Thomson's atomic model. Thomson's atomic model. What does Thomson's atomic model say? He said atom is like a watermelon. He said atom is like a watermelon. Seeds represent the electrons. Okay, the seeds inside this watermelon means electrons. And red portion that we eat represents the positive charge. This red portion means positive charge. He said positive charge is distributed like this. And he said an atom is electrically neutral. What does that mean? Number of positive charge is equal to the number of negative charge. Okay. And he also said in an atom, positive charge and mass of the sphere is uniformly distributed. Means positive charge is equally distributed at every point. It's not like, sir, it is more positive charge here, less positive charge here. No, it is uniformly distributed, equally distributed. Similarly, mass is also uniformly distributed. Then we have the next one, that is Rutherford's atomic model. Rutherford's atomic model. What does Rutherford atomic model say? Basically, he performed an experiment that is called alpha particle scattering experiment. Okay, based on this experiment he performed, he basically gave us the atomic model. What does he do? What did he do? He took an alpha source. Alpha source means that is source of alpha particles. Okay, this is the source of alpha particles from which alpha particles are coming out. Okay, now guys, so basically from this source of alpha particles, we say beam of alpha particle is coming out. Beam of alpha particles. Beam of alpha particles means large number of alpha particles are coming out. Large number of alpha particles are coming out. And when large number of alpha particles are coming out, they are passing, and he placed a gold foil over here. Gold foil over here. It is like gold atom. He placed a gold foil over here. Okay. Then, my dear friends, these alpha particles cross this gold atom or foil and have fallen on the screen. This is the deflection screen. Now, guys, once he did this experiment, he basically said 99.8% alpha particles are directly crossing and falling on the screen. 99.8% alpha particles are directly crossing this gold foil and falling on the screen. Here, directly. Only 0.14% were deviating. Only how many percent? 0.14%. That could be an error also. Means all the alpha particles are directly crossing the gold foil. Means 1 in 8,000 alpha particles were deviated or reflected back. Means if you are sending 8,000 alpha particles, only 1 is deviated. This was okay. Now guys, listen to me very carefully. Listen to me very carefully. What does this model actually say? Let me just give you the feel of this model. See. So basically, this person, Rutherford, he said, if this is an atom, Thomson said positive charge is present in the entire sphere, in the entire atom. But Rutherford said, when I performed the experiment, alpha particles are directly crossing the gold foil, directly crossing this atom. Okay. Alpha particle means positive charge. Why? Because alpha particle has 2 protons, 2 neutrons. So it has positive charge. He said if positive charge was present in the entire atom, then these particles, alpha particles, would have been repelled. They would have deviated, something like this. At least 70-80% would have deviated. If not 80%, 30% would have deviated. But how many deviated? How many were deviated? Only 0.14%. So what does that say? That says positive charge is not present in the entire atom. It is present at a unique position that is called a nucleus. So if there is an alpha particle which is something like this, okay, which if it falls on the nucleus, it only will be reflected back. So this is that one alpha particle, 1 in 8,000 which was reflected back. Rest of the alpha particles will directly cross. So he said positive charge, this gives us the indication positive charge is not present in the entire sphere. It is present at a unique position. Okay, it is present at a unique position. Now see, according to this model, positive charge is concentrated at a unique position called a nucleus. Electrons are revolving around the nucleus but are randomly distributed. But are not randomly distributed. Okay. So basically this person, he said, if positive charge is present in the entire atom, now if you are sending the alpha particle, it should be deviated, but it is not deviating, means it is not present in the entire atom. Positive charge is present at a particular position, that's called a nucleus. And like he said, in a watermelon, electrons are randomly distributed. No, he said electrons are revolving around the nucleus, but are not randomly distributed, like Thomson said. Okay. This was the Thomson's atomic model. Now guys, drawbacks of Rutherford's, this was the Rutherford's model. Drawbacks of Rutherford's atomic model. Guys, it could not explain the stability of an atom. It could not explain the stability of an atom. What does that mean? See, there is a concept. If charge revolves, there is a concept. If charge revolves, we say charge accelerates. Revolving of charge means charge is accelerating. And if charge is accelerating, electromagnetic wave is, see. If electron is revolving means charge is revolving. Charge is revolving means charge is performing the circular motion. Circular motion is an accelerated motion. Means charge is accelerating. If charge is accelerating means electromagnetic wave is produced because source of electromagnetic wave is accelerated charge. Okay. And if electromagnetic wave is produced means energy is radiated. Energy is released. Energy is lost. Energy is radiated. Energy is lost. Okay. Means electron falls into the nucleus. Means electron falls into the nucleus. So basically, if an electron is revolving around the nucleus, it is losing the energy. If it is losing the energy, this positive charge nucleus, it will keep on attracting it, it will keep on attracting it, and the time will reach, it will collapse into the nucleus. Okay, so what does that mean? What does that mean? What does that mean? That means according to this, atom is unstable. But we know atom is stable. Atom is a stable system. Electron does not collapse into the nucleus. So when these questions were asked to Rutherford, he couldn't answer. That's why it became his drawback. That's why it became his drawback. Then comes the Bohr's postulate. Then comes the Bohr's model of atom. Guys, tell me in the chats, is this clear till over here? Is this clear till over here? Quickly, guys. Quickly, guys. Okay, guys. Is this clear? Now, guys, then comes the Bohr's model of atom. In the Bohr's model of atom, you have got the Bohr's first postulate. You have got the Bohr's first postulate. What does Bohr's first postulate mean? What does Bohr's first postulate mean? Bohr's first postulate means, guys, like Rutherford couldn't answer these questions. People asked him, electron is revolving means electron is accelerating, charge is accelerating, means EM wave is producing, energy is radiating, electron will fall into the nucleus. So Bohr said, no doubt electron is revolving. Yes. Okay. It is an accelerated motion. Yes. Charge is accelerating. Yes. Forms wave. Yes. But it does not form the EM wave. It forms stationary wave. Stationary wave is that wave. Stationary wave is that wave which does not radiate, which does not lose energy. It does not lose energy. It does not radiate energy. Okay. So this was the Bohr's first postulate. This was the Bohr's first postulate. Then came the Bohr's second postulate. Bohr gave his model in 3 postulates. This is the second postulate. Bohr's second postulate defines stable orbits. He said, an electron, Bohr said, electron is not revolving in the random orbits like this is the nucleus. Rutherford said it is revolving in the orbits. In any orbit it can revolve. Bohr said no. It will only revolve in those orbits. Orbit means path in which its angular momentum is nh by 2 pi. Value of n can be 1, 2, 3 and so on. So if I say an electron is revolving in an orbit in which its angular momentum is 1h by 2 pi, is it true? We say yes. Why? Because value of n is 1. So 2h by 2 pi, yes. 3h by 2 pi, yes. Okay. So basically, an electron can revolve only in those orbits in which its angular momentum is nh by 2 pi. N can be 1, 2, 3 and so on. Keep this thing in your mind. Okay, in which its angular momentum is some integral multiple of h divided by 2 pi. Bohr's third postulate. Bohr's third postulate. If, guys, Bohr's first postulate says that, let's suppose an electron is revolving in an orbit. If it makes the transition from lower orbit to the higher orbit, means, if we want to make this electron to go from lower to higher orbit, we have to supply the energy to it. Okay. If an electron makes the transition from higher orbit to lower orbit, energy is released. Means if an electron is moving from higher orbit to lower orbit, in that case, energy is radiated, energy is released. If it has to make the transition from lower orbit to higher orbit, energy has to be supplied to it. In that case, we need to supply the energy. Then only it can move from lower orbit to higher orbit. Okay. If it moves from higher orbit to lower orbit, energy is released in that case. Okay. Yes. Now we need to talk about mathematical analysis of Bohr's theory. I hope you got the feel. First postulate says that electron revolves around the nucleus. Okay. It is an accelerated motion. It forms the wave, but it forms stationary wave, which does not release the energies. Hence, atom is stable. Second says that an electron revolves only in those orbits in which its angular momentum is nh by 2 pi. Third says, if an electron makes the transition from higher orbit to lower orbit, energy is released. If we want to make the transition from lower to higher, we need to supply the energy. Mathematical analysis of Bohr's theory. Guys, understand one thing very carefully. I'm saying over here, this is the nucleus. This is the nucleus. Nucleus is at the center. What is the charge on nucleus? We say, sir, Z. Z is the atomic number. Like for hydrogen, atomic number is 1, Z is 1. For helium, it is 2. For lithium, it is 3. Okay. So basically, this is the charge of the nucleus. This is the charge of the nucleus, Z. Okay. And this is the radius. Electron is revolving in our radius, okay, in this path. This is the electron. It has got velocity v. Now, if somebody says, what is the velocity of an electron in the nth orbit? Like if I am saying this orbit over here, this is the nth orbit. If I am saying this is the nth orbit. Okay. So in this nth orbit, what is the velocity of an electron? Velocity of an electron in the nth orbit is v is equal to 2.2 into 10 raised power 6 z divided by n. What is the z? Z is atomic number. Z is atomic number. Okay. And what is n? N is the nth orbit. So if somebody asks you, what is the velocity of an electron in the nth orbit? 2.2 into 10 raised power 6 z by n. Or you can say v naught z by n. So this is the velocity of an electron in the nth orbit. This is the velocity of an electron in the nth orbit. This is the velocity of an electron in the nth orbit. Okay. Okay. Now guys, take a look. Radius of an electron in nth orbit. Let's suppose this is the Z. And here electron is revolving. Its mass is m, its charge is e. What will be the radius of the electron in the nth orbit? Guys, this is r is equal to 0.53 angstrom n square by z. We say this is the radius of electron in the nth orbit. We can say r is equal to r naught z n square by z. R is equal to r naught n square by z. This is the radius of an electron in the nth orbit. Okay. Then take a look. Find the radius of Li2 positive ion in its ground state, assuming Bohr's model to be valid. Guys, when it comes to Li2 positive, we say atomic number Z is 3. We are supposed to find the radius. We say radius is r is equal to r naught n square divided by z. R is equal to, we say 0.53 angstrom. Okay. Or we say 0.53 into 10 raised power minus 10 if you convert to the meters, n square by z. Ground state means the first orbit, means ground state n is 1. So it is 1 square divided by, we say 3. Okay. Solve and get the answer. Next, find the maximum speed of the electron of a hydrogen atom in its stationary orbit. Okay, maximum angular speed means you have to find the omega. Guys, we say V is equal to R omega. You might have studied this formula. Can I say here omega will be equals to V divided by R? It says find the maximum angular speed of an electron in the hydrogen atom. We say for hydrogen atom, always remember value of Z is 1. And if it is talking about stationary orbit, means first orbit, N is 1. Z is 1, N is 1. Now, can I write this as omega will be V is equal to, that is 2 into 10 raised power 6. What is the velocity of an electron in the nth orbit? 2.2 into 10 raised power 6. So, I'll write over here. This is 2.2 into 10 raised power 6. Okay. This will be exactly, that is Z by N divided by, this is 0.53 into 10 raised power minus 10. Then we say N square divided by Z, N square by Z. Okay. So this is omega. So I can say this omega will come out to be 2.2 in 10 raised power 6. Guys, see, omega will come out to be 2.2 into 10 raised power 6 Z by N. Z is 1 divided by 1 upon 0.53 into 10 raised power minus 10, 1 by 1. Further, if you solve it, so omega will come out to be, this is 10 raised power minus 10, it becomes 10 raised power plus 10. So 2.2 into 0.53, check it guys. So 4.1 into 10 raised power 16 radian per second. Please check its answer from your end. Approach is correct. Now take a look in this. Time period of revolution of an electron in the nth orbit. Time period of revolution of an electron in the nth orbit. Now guys, time period of revolution of an electron in the nth orbit. Time period of revolution of an electron in the nth orbit. Now guys, this is the nucleus over here. Its charge is, we say, Z. At R radius, you have got an electron. At R radius, you have got an electron. We say an electron is revolving in the nth orbit. I'm saying, guys, how much time it is going to take in completing one cycle. That is how much time an electron takes to complete one cycle is called the time period. So that time period, my dear friends, it is going to be 1.51 into 10 raised power minus 16 n cube divided by Z square. So this will be the time period of an electron in an nth orbit. Now guys, magnetic field at the center of an atom due to the revolution of an electron. Guys, when, listen. The concept is, let's suppose this is the nucleus, Z. An electron revolves around the nucleus. Always remember, when it comes to an electron, it revolves around the nucleus. when it comes to an electron, it is revolving around the nucleus. Okay. Okay. When it comes to an electron, okay. When it comes to an electron, it revolves around the nucleus. Okay. Yes. Now, if I'm saying in this particular case, guys, electron moves means current is being produced. So now this current is in the loop, because electron moves in a circle. So current is produced in the loop. Due to this current, magnetic field will be produced at the center. Because whenever current flows in a loop, magnetic field is produced. And that magnetic field will be this. B is equal to B naught Z cube divided by N raised power 5. And value of B naught is 9.27 into 10 raised power minus 24 joule per Tesla. So this will be the value of magnetic field at the center of an atom. Because whenever current flows, magnetic field is produced. Here, due to the moving of electron, current is flowing. Due to that current, magnetic field is being produced. That is the magnetic field. Okay. This one. Take a look at this. Take a look at this, guys. See, total energy of an electron in nth orbit. Total energy of an electron in nth orbit. Total energy of an electron in nth orbit. My dear friends, what I'm trying to say in this particular case is, you have got a nucleus that is ZD. You have got a nucleus that is ZD. And an electron is revolving around its nucleus, okay? As always remember, this electron has a mass, it has charge, it is moving with a velocity v. If there is a mass which has velocity v, it has kinetic energy. Because when there is a mass moving with some velocity, it has kinetic energy. So we say kinetic energy of an electron, here it will be Ze square upon 8 pi epsilon naught r. Z is the atomic number, E is the charge on an electron, 8 pi epsilon naught r. R is the radius. Okay. And always remember, this kinetic energy is positive, guys. This kinetic energy is positive. Okay. 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 Yes. Now, guys, what I'm trying to say here is, in this particular case, whenever you have got a nucleus over here, guys. This is the electron, this is the nucleus. This is the electron, this is the nucleus. Okay. Okay. So don't write it like this, it will confuse you. And I'll solve the question on this one. Okay. Okay, now take a look. Now take a look. Guys, this is the electron, this is the charge ZD. If this is the charge, this is another charge. We have studied whenever there are two charges placed at some separation, they have potential energy. So here, potential energy will be minus Ze square upon 4 pi epsilon naught r. Okay, this kinetic, this is potential. And when it comes to the total energy is kinetic plus potential. That is minus Ze square upon 8 pi epsilon naught r. Minus Ze square upon 8 pi epsilon naught r. Minus Ze square upon 8 pi epsilon naught. Okay, guys. If you talk about kinetic energy and R, it is inverse relation and it is positive. If you make the graph between kinetic energy and R, so it is like this. Kinetic energy is inversely proportional to R, and this kinetic energy, my dear friends, it is positive. When it comes to the potential energy, remember, potential energy is negative. Potential energy is negative. Total is negative. That's why graph of potential energy is from lower side. Graph of total is from lower side. Okay. And graph of total energy will be bit here in between and potential and kinetic energy. Keep this thing in your mind. Okay. Now, guys, see. I want you to understand one thing. What is the formula of total energy? We say as total energy is minus Ze square upon 8 pi epsilon naught r. 8 pi epsilon naught r. Guys, can I write it like this? This will be minus ZE square upon, we say 8 pi epsilon naught. What is the value of R? This is R naught n square by Z. Z will go in the numerator. Okay. So this will become minus E square upon 8 pi epsilon naught R naught. Then we say Z square divided by n square. Guys. When you put the value of E, when you put the value of epsilon, when you put the value of, sorry, E pi epsilon naught R naught, epsilon naught is 8.85 into 10 raised to power minus 12, 3.14. R naught is 0.53 into 10 raised to power minus 12. Charge on an electron is 1.6 into 10 raised to power minus 19. And when you solve it, it will come out to be minus 13.6 Z square by n square. This will be the total energy. So that is mentioned exactly over here. Minus 13.6 Z square by n square. Then we say for hydrogen atom, what is the value of Z1? So put Z1 over here. Total energy will be minus 13.6 by n square. And if you see over here, kinetic energy and total energy are exactly same. But this is negative, this is positive. Negative and positive. This is negative and this is positive. So if kinetic energy and total energy are exactly same, but kinetic energy is positive, this is negative. So here it will be exactly same, but this is positive. But this is positive. Tell me quickly in the chats, is this clear? Tell me quickly in the chats, is this clear? Now guys, let's move on to the next one. Okay. Some important graphs I want you to understand here. Graphs related to total energy. Guys, see, we see total energy is minus 13.6 Z square by n square. Let's suppose if Z is constant. If Z is constant. Can I say in that particular case, relation between total energy and n, it is E is inversely proportional to n square. But energy is negative. If I say E is inversely proportional to n square and E is positive, total energy is positive, graph would have been something like this. This is the graph of inverse rectangular hyperbola. Okay. But energy is negative, we'll copy the same graph, but something like this. Okay. Now see, if we make the graph between E versus 1 by n square. So when you are making the graph E versus n square, okay, so it is inverse. So it will be something like this. But when you make the graph between this and this, here power of this is 1, here power of this is 1. So it will be the straight line. If it was positive, straight line from the upper side. But it is negative, so I'll make the straight line from the lower side. So whenever you make, if you put E on this, 1 by n directly on this, so means power of this is 1, power of this is 1. So graph would be straight line. Since it is negative, that's why I'm making it from the negative side. Now see, if you say n is constant, let's assume n is constant, 13.6 is constant, total energy is directly proportional to E is directly proportional to Z square. So E is directly proportional to Z square. See, now if this is E, this is Z. If you directly put Z square over here, so it would be its power is 1, its power is 1. So graph would be straight line, but since energy is negative, so graph would be straight line from the lower side. Now take a look here. If you put Z here on this, it will be Z. E is proportional to Z square. Understand this carefully. So E is negative. Guys, if E was positive, graph would have been something like this. Okay? Upward parabola. But since E is negative, same graph will copy from the lower side. This would be the graph. I hope you understood these graphs. Okay? Okay. Next we say, guys, for a hydrogen atom, we need to write the energy. What is the value of energy? Total energy is minus 13.6. Okay. For hydrogen, Z is 1, so I'll directly write divided by n square. Minus 13.6 Z square by n square. Z is 1, so directly n square. This is the total energy. Now, what I'm trying to say in this particular case, guys, if an electron is revolving in the first orbit, okay, means for first orbit n is 1. That is called ground state. Its energy would be 13.6 divided by 1. That would be minus 13.6. If an electron is revolving in the second orbit, that is the second n is 2. So means first excited state. Either you call it the second orbit or first excited state. So I say that would be minus 13.6 divided by 2 square. That is 4. Minus 13.6 divided by 4. That would be minus 3.4. If an electron is revolving in the third orbit, okay, that is second excited state or third orbit. So put 3 here. 3 square is 9. Minus 13.6 divided by 9. So it would be minus 1.51 electron volts. If an electron is revolving in the fourth orbit, so put 4 here. So 4 square is 16. Minus 13.6 divided by 16. It would be minus 0.85. Next would be minus 0.36 and so on. Okay. So these are the energies in different orbits of a hydrogen atom for an electron. Take a look. There is a question. The total energy of an electron in an orbit is minus 3.4. The total energy of an electron in an orbit is minus 3.4. Total energy is given as minus 3.4 electron volts. Its kinetic and potential are, guys, if total is this much, don't you think kinetic will be exactly 3.4 electron volts but positive? Because kinetic and total are equal. Okay, but kinetic is positive. And when it comes to the total energy, we say it is simply kinetic energy plus potential energy. You have to find potential, take it here. So total energy minus, I can say kinetic energy, it will be equals to potential energy. Total energy is how much? Minus 3.4. This would be minus kinetic energy is how much? Minus 3.4. It would be potential energy. So I can say potential energy will come to minus 6.8 electron volts. Minus 3.4 minus 6.8. Sorry, plus 3.4 minus 6.8. Take a look at this. The electron in an hydrogen atom jumps from excited state n is equal to 3 to its ground state n is equal to 1. Yes, kinetic positive, potential negative. The electron in a hydrogen atom jumps from excited state n is equal to 3 to n is equal to 1. See guys. An electron is revolving. This is the, let's suppose this is the nucleus, ZD. An electron is revolving in the third orbit. An electron in a hydrogen atom jumps from n is equal to 3 to n is equal to 1. An electron jumps from n is equal to 3 to n is equal to 1. N is equal to 1. N is equal to 3 to n is equal to 1. Okay? N is equal to 3 to n is equal to 1. Thus, and the photons thus emitted falls. Okay. Guys, see. When an electron jumps from n is equal to 3 to n is equal to 1, we say energy is released. Energy is released in the form of what? We say energy is released here in the form of photon. So this is the photon which comes out. Okay. Then it says this photon further falls on a photosensitive metallic surface. This falls on the photosensitive metallic surface. Okay. Okay, this is photosensitive metallic surface. Metallic surface. This is photosensitive metallic surface. Now, if this falls on the photosensitive metallic surface, I would want you guys to focus over here. If this falls onto the photosensitive metallic surface, we say electron is thus emitted. Electron is emitted. Okay, electron is emitted. This is the electron which is emitted. Because photoelectric effect will take place when photon falls onto the metal surface, photoelectric effect takes place. Okay. And we have to find the work function of this material. We have to find the work function of this material. See guys, first of all, when electron moves from higher orbit to lower orbit, photon is released, means energy is released. Oh, we say energy of photon released will be, always remember, energy of photon will be, what is the energy of electron in the higher orbit? In this higher orbit, that is n is equal to 3. So it is, what is the energy of an electron in third? Minus 1.51. What is the energy of an electron in the first orbit? That is minus 13.6. Okay. So it would be, what is the energy difference over here? Energy difference, delta E. That is minus 1.51. Okay. Okay. Higher energy state. Okay. Then it would be minus of minus 13.6. Okay. So this would be 12.1. Okay. In this particular case. Okay. Minus 13.6. Okay. It is saying from n is equal to 3 to n is equal to 1. So here it is minus 1.51. Yeah. 12.1. Now, my dear friends, if I am saying an electron moves from higher orbit to the lower orbit. If I am saying, okay, we are supposed to find stopping potential. Let's find stopping potential. V naught. Work function of this metal surface is given as 5.1 electron volt. Okay. Yes. So now what is the energy of the electron over here? Energy of a photon over here. So when electron moves from n is equal to 3 to n is equal to 1, what is the energy here? Minus 1.51. What is the energy over here? Minus 13.6. So can I say in this particular case, energy would be, guys, that is E2 minus E1. Energy of an electron here minus energy of an electron here, that would be 12.1 electron volts. Now this is the energy of a photon. Energy of photon is equal to the energy gap between the two. Now can I say energy of photon will be equals to the work function plus kinetic energy maximum. Okay. Now energy of photon is equal to how much? That is 12.1 is equal to work function is 5.1 plus kinetic energy maximum. It is going to be EV naught. Now 12.1 electron volt minus 5.1 electron volt. 12 minus 5.1. So this will be 7 electron volt will be equals to EV naught. E and E will cancel. Stopping potential V naught will be equals to 7 volt. Yes, it is 7 volt. This is a good question actually. Now, consider third orbit of He positive. Using the non-relativistic approach, the velocity of an electron in this orbit will be. Guys, when it comes to the He, value of Z will be equals to 2. And it says third orbit means n is equal to 3. Velocity of an electron, we are supposed to say velocity of electron is V naught Z by n. So V is equal 2.2 into 10 raised power 6. Value observed is 2. This will be 3. Now solve this and get the answer. Spectrum. Spectrum. Is this clear, guys? Tell me. Is this clear? Guys, smash the like button if you have not liked this session yet. Now, guys, spectrum. What does spectrum mean? It is the collection of radiations of different wavelength on a photographic plate, or it is the image produced on a photographic plate. Guys, see, I'll give you the crystal clear feel of the spectrum. Let's suppose this is a white light. Okay, this is a white light. White light. This is a white light coming. And we'll place a prism over here. We'll place a prism. Whenever white light enters the prism, we say it is divided into, you can say it something like that, 7 different colors. Okay. First one will be violet, indigo, blue, green, yellow, orange, red. VIBGYOR. Okay. Now, when it then we place over here a photographic plate, or you call this as spectrum. So my dear friends, we say this violet falls here, it creates the violet spot. This creates indigo spot. This creates blue spot. This creates green spot, yellow spot, orange spot, red spot. So this creation of these spots, creation of these images, all of these will have different wavelength, because violet has different, yellow has different, indigo has different. So this creation of these spots on a photographic plate, it is called spectrum. It is called spectrum. As simple as that. Then let's talk about absorption. There are 2 types of spectrum: absorption spectrum, emission spectrum. See. Let's suppose there's a screen over here. Okay. And my dear friends, you take this an atom. This is the nucleus and this is the electron revolving. Let's suppose you are sending a photon. Understand this very carefully. It means light. Light is photon. And my dear friends, if you are sending a photon over here, what is the energy of an electron in the first orbit? What is the energy of an electron in the first orbit? 13-13.6 electron volts. What is the energy of an electron in the second orbit? -3.4 electron volts. What is the energy gap between the two? That is 10.2. 13.6 minus 3.4, that will be 10.2. Now you are sending a photon of energy 10.2 electron volts. Okay, it goes, and this electron absorbs this energy or this photon. Photon is energy. It will absorb it. When it absorbs this 10.2 electron volt energy, it makes the transition from first orbit to the second orbit. It makes the transition from first orbit to the second orbit. When it makes the transition from first orbit to the second orbit, we say here, a line is being created. Okay, a dark spot is being created. This dark spot represents that electron has been absorbed by, photon has been absorbed by the electron. Photon has been absorbed by the electron. So on the bright background, okay, a dark spot is being created. Dark spot gives you the idea that this photon has absorbed this electron has absorbed the photon. Okay, then only it made the transition from lower orbit to the higher orbit. This kind of spectrum is called absorption spectrum. Absorption means in which an electron absorbs the light, absorbs the photon, then makes the transition to the higher orbits. So that is called absorption spectrum. When it comes to the emission spectrum, let's suppose if an electron is revolving in the second orbit, it makes the transition from second to first. We know when electron moves from higher orbit to lower orbit, photon is released, energy is released. That photon then falls onto the screen. If we place a screen over here, photographic plate. Now, if this photon has the wavelength equal to the wavelength of yellow, then the yellow spot will be created. If this photon has the wavelength equal to the wavelength of red, then the red spot will be created. If this photon has the wavelength equal to the wavelength of indigo, indigo spot will be created. Now when an electron makes the transition from higher orbit to lower orbit, releasing of photon, then falling on the screen, on the dark screen, bright spots are formed. This is called emission spectrum. So in case of emission spectrum, electron moves from higher orbit to lower orbit. Then photon is released, which then further falls onto the screen. Okay, and bright spots are created. Bright spots are created. Okay, bright spots are created. Now guys, listen, this is called what? Emission spectrum. So in case of emission spectrum, electron moves from higher orbit to lower orbit. In case of absorption spectrum, electron moves from lower orbit to higher orbit. Then let's talk about the different spectral series. When it comes to the spectral series, we show this transition of electron from higher orbit to the lower orbit on spectral series. Like here, it is the real life physical field. But if you have to show the same situation on spectral series, we show it in the spectral series like this. First series that we need to learn over here, that is Lyman series or K series. Lyman series or K series. Take a look. When it comes to the Lyman series or K series, I want you to understand one thing. See guys, when an electron moves from higher orbits to first orbit, we show it on the Lyman series. So basically, this transition that you show over there in photographic plate, you have to show that here in the Lyman series. Now see, how do we show it? In case of Lyman series or spectral series, we make the orbits with the help of straight lines. This is the first orbit. This is the second orbit, third orbit, fourth orbit, fifth orbit, and this is nth orbit. Now, if an electron makes the transition from n is equal to 2 to n is equal to 1, if an electron makes the transition from n is equal to 3 to n is equal to 1, if an electron makes the transition from n is equal to 4 to n is equal to 1, if an electron makes the transition from n is equal to, we say 5 to n is equal to 1, if an electron makes the transition from n is equal to infinity to n is equal to 1. Okay. So we show it with the help of this line. If it makes from 2 to 1, we show it with this line. This is called first line of Lyman series, and this is K alpha. This is second line of Lyman series, K beta. Third line of Lyman series, K gamma. So basically, when an electron makes the transition from higher orbit to lower orbit, from second to first, we say a line is formed. Photon is released, a line is formed. This line in spectral series, we show it like this. Okay, we show it like this. Okay, we show it like this. This third line would be from here. This is not the third line. This is the third line. This is the third line. Okay. This is the third line. Okay. Now, my dear friends, listen to me very carefully. If I say, sir, if an electron makes the transition from here to here, what will be the energy gap? Energy in this is minus 3.4. Energy in this is minus 13.6. Okay. Don't you think energy gap, this energy gap is less as compared to this energy gap? Because here it is 13.6 minus 1.51. Here it is 13.6 minus 3.4. So energy gap would be less than this. Then this energy gap would be more. Means this first line will have minimum energy. Okay. If energy is minimum, frequency would be minimum. Because when it comes to the energy, we say it is Hc or H into F. Or we say it is Hc divided by lambda. Directly proportional to frequency, inversely proportional to lambda. So this first line will have maximum wavelength. And last line, it will have, we say maximum energy, maximum frequency, and we say minimum wavelength. Okay. This is how we show in the Lyman series. Then we say bracket series. Okay, first, oh, this is Bohr series. When it comes to the Bohr series, guys, if an electron makes the transition from here, I'll write, we say here final orbit is 2, initial orbit is 3, 4, 5, and so on. So means if an electron makes the transition from higher orbits to second orbit, if an electron makes the transition from higher orbits to second orbit, we show that in Bohr series. Okay. So this is the first line of Bohr series. This is the second line of Bohr series. This is the third line of Bohr series. This is the last line of Bohr series. This would be the ground state. This would be the second orbit. This would be the third orbit. This is the fourth orbit, fifth orbit. So here also, first line will have the maximum wavelength, minimum frequency, minimum energy. And last line will have the maximum energy, maximum frequency, minimum wavelength. So in case of Bohr series, if an electron makes the transition from higher to lower, we show it in Bohr series. Similarly, when it comes to the Paschen series, here, N final is third orbit. Finally, orbit is, so we say when an electron makes the transition from higher orbits to the third orbit, we show that in Paschen series. Okay, and initial can be 4, 5, 6 to infinity. So this is the Paschen series. Then, okay. Similarly, you have bracket series, P-fund series. Now, I want you to understand this very carefully. You say, when an electron makes the transition from higher orbit to the lower orbit, photon is emitted. That photon will have some wavelength. We say photon is emitted, that photon will have some wavelength. Yes. If somebody asks you, what is the wavelength of that photon? Guys, this would be the wavelength. Instead of all these, you replace it with the Rydberg constant. Okay. So guys, if I'm saying an electron makes the transition from higher orbit to the lower orbit, we say in that case photon is released. This photon will have wavelength. How do we calculate that wavelength? 1 by lambda r into 1 by n final. Final means final, n final means final orbit, minus 1 by initial. Initial means initial orbit. Lambda is the de Broglie's wavelength. Okay, 1 by lambda. Now guys, I want you to understand, or a wavelength directly you say. R will be Rydberg constant 1.03 in 10 raised power 7 meter inverse, or 1 by R will be, and 1 by lambda is wave number. Guys, 1 divided by lambda here is wave number. Okay. And we say lambda is wavelength. Lambda itself is wavelength. Now take a look at a question which was asked in 2017. The ratio of wavelength of the last line of Bohr series. Last line of Bohr series. Guys, come here. Last line of Bohr series is this, in which n initial is infinity, n final is 2. I'll write over here. We have to find its wavelength. See, last line of Bohr series. Guys, take a look. So, guys, for last line, we say n initial, that is infinity. Last line means if an electron makes a transition from infinity to 2, infinity to 2. So, n initial in this case will be 2. N initial in this case will be 2. Okay. So, now tell me, 1 divided by, take a look, 1 divided by lambda will be equals to, 1 divided by lambda will be equals to, that is our Rydberg constant, 1 by n final square minus 1 by n initial square. So 1 divided by lambda, okay, this is Bohr, 1 by lambda Bohr, it will come out to be Rydberg constant, that is R. Now guys, 1 by n final, that is 1 by 2 square, that is 4. Okay, this is n final. Minus 1 divided by infinity, that is 0. So that is 1 divided by lambda Bohr will be equals to R divided by 4. Okay. Now further you can say here, guys, lambda Bohr will be equals to 4 divided by R. Okay. What I want you to understand in this particular case, that is, we say last line of Bohr series and the last line of Lyman series. Okay. When it comes to the last line of Lyman series, guys, for the last line, we say n initial will be infinity. Okay. N final will be 1. N initial will be infinity and n final will be 1. So how can we write 1 divided by, we say lambda Lyman, it will be Rydberg constant, 1 by n final square, n final is 1, 1 by 1, minus 1 by infinity. Infinity is 1 by infinity is 0. So this will be 1 by lambda Lyman, it will be R. So lambda Lyman will be 1 by R. Okay. Now tell me, guys, I can say in this particular case, lambda Bohr, we are supposed to find the last line, ratio of last line of Bohr upon Lyman. It will be, that is 4 divided by R upon 1 divided by R. R and R will cancel, so it is 4:1. So ratio in this case is 4:1. Okay. Now let's move on to the next chapter, that is nuclei. Tell me guys, is this clear? Is this clear? Last chapter of modern physics. Is this clear? Please tell me in the chats. We'll take the break exactly at 10 o'clock. We'll take the break exactly at 10 o'clock. Let's finish this chapter till 10 o'clock. Chapter Nuclei. Okay. We'll take the break exactly at 10 o'clock. Please, 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 please. We need to finish all of these chapters, guys. Okay, we'll take the break exactly at 10 o'clock. Okay. Let's take a look. Till 10, we will finish this chapter. Let's take a look at this chapter. Nuclei. Guys, till now we were studying the complete atom. Right now I am studying the nucleus. Nucleus is present at the center of the atom. Like this, the atom. At the center of the nucleus, it has got, at the center of the atom, it has got nucleus. Okay. As always, remember, radius of atom is 10 raised power minus 10 meter. Radius of nucleus is 10 raised power minus 15 meters. Guys, when it comes to the nucleus, if people ask you, what is present inside the nucleus? Always remember, inside the nucleus you have got protons, inside the nucleus you have got neutrons. So inside the nucleus there are two types of particles, that is protons and neutrons. And protons have got positive charge. Okay, when it comes to the protons, everybody knows they have got positive charge. When it comes to the neutrons, we say they are neutral. And when it comes to the electrons, they have got negative charge. Now take a look. Take a look. The particles which are present inside the nucleus, the particles which are present inside the nucleus are called nucleons, hydrons or baryons. Those particles which are present inside the nucleus are called, we say, nucleons, hydrons or baryons. So means these protons and neutrons are nucleons. Representation of a nucleus. Guys, how do you exactly show nucleus? Let's suppose I'm saying, sir, this is a nucleus. How do you say? This nucleus will have its name, let's suppose X, okay? On top of it, we write A, here we write Z. What is A? A means mass number. Mass number means number of protons plus number of neutrons. If I say this is a nucleus, it has got 5 protons, 5 neutrons. So its mass number would be 10. And Z means atomic number. Atomic number means number of protons only. Like, let's suppose this is a nucleus. In this nucleus, you have P, 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 N, N, N. 3 protons, 3 neutrons. We say name of this is X, let's suppose. And mass number in this particular case will be 6. Atomic number in this case will be 3. Number of protons is 3. Number of protons plus neutrons is 6. Even if you have to find the number of neutrons, that will be A minus Z, 6 minus 3. So that will be 3. Number of neutrons will be A minus Z, 6 minus 3. Okay. Okay. Then neutrino. Neutrino, there are different types of particles. The first one is neutrino. It is a neutral particle. Neutral particle. It is a neutral particle. Okay. Mass less than mass of electron. We say almost mass of this neutrino is much less than mass of electron. Okay. Then you have alpha particle. Alpha particle is made up of, it is 2 protons plus 2 neutrons. Okay. So when it comes to the mass of alpha particles, we say it is 4 times mass of proton, because 2 protons have mass 2m, 2 neutrons have mass 2m, 2m plus 2m is 4m. And when it comes to the charge, guys, 2 protons have charge, but 2 neutrons does not have charge. So we say its charge is 2e. 2 protons will have charge. Charge on a proton is E. E plus E is 2e. So beta particle, it is an electron beam. Electron beam. What does that mean? That is fastest, like you say, beam of alpha particles. Fastest moving electron. Okay. And then you have positron. Okay. It is the antiparticle. Antiparticle of electron. Okay. When it comes to charge same as proton. This is that particle which has the same charge as proton. But when it comes to the mass we say mass of positron will be equals to the mass of electron. Its mass is not equal to the mass of proton. Its mass is equal to the mass of electron. Keep that thing in your mind. Okay, take a look, guys. Then basically you have got up quarks and down quarks. Okay, up quarks and down quarks. You have got quarks. There are 6 types of quarks. Okay, up quark, top quark, beauty quark, down, bottom, charm. So basically when it comes to the proton, when it comes to the neutron, proton and neutron both are made up of quarks. When different number of quarks join together, they form proton and they form neutron. Keep this thing in your mind. So we say when it comes to the quark, charge on a proton quark, up quark is 2 by 3e. Top quark 2 by 3e. Beauty quark 2 by 3e. When it comes to the down quark, charge on the down quark is minus 1 by 3e. Charge on the bottom quark is minus 1 by 3e. Charge on the charm quark is minus 1 by 3e. Okay. This is the charge. Okay. Okay. So this is the charge on up quark, top quark, beauty quark. Down quark, bottom quark, charm quark. Minus 1 by 3, minus 1 by 3, minus 1 by 3. Now guys, rest mass energy. You might have studied till now kinetic energy. How do you define kinetic energy? You say, sir, kinetic energy is, let's suppose you have a mass. It is moving with a velocity v. So this mass will have kinetic energy, that is 1 by 2 mv square. Mass kinetic energy is simply what? 1 by 2 mv square. So we say this kinetic energy, this is due to the motion. Due to the motion. So whenever a particle comes in motion, it has kinetic energy. Even you define potential energy also. Let's suppose this is a particle. You take it to the height h. We say its potential energy is mgh. How do you define potential energy? When you take an object to the height h, you define because of the height h, it has potential energy. Because of the motion, it has kinetic energy. Okay. Now, what does rest mass energy mean? Let's suppose this is a mass. We say due to the mass of an object, it has energy associated with it. That is called rest mass energy. Like this pen, it has mass. Sir, does this mass have Rest mass energy, yes. This mass has rest mass energy. Okay. Why? Because it has mass. Whenever there is mass, it has rest mass energy. And that rest mass energy will be E is equal to mc square. E is equal to mc square. Okay. M is the mass of that object, C is the speed of light. So let's suppose if an object, its mass is, let's suppose 10 kg. If somebody asks you, find the energy associated in this, find the energy in this, you say E is equal to, that is 10 into C square. C is the speed of light, that is 3 into 10 raised power 8, its square. So energy will come out to be 10. 3 square is 9 into 10 raised power 8 ka whole square, that is 16. So this will be 90 or 9 into 10 raised power 17 joules. So this much of energy is present in 10 kg mass. And this is so huge. This is so huge that it can burn the entire universe, galaxies, everything. This much of energy is so huge, it can burn the planets, entire universe. Okay. Okay. Are you able to understand? So this is the mass present in 10 kg only. Now you imagine mass present in 100 kgs. Mass present in 1000 kgs. That is extremely huge. Do you know how much mass was converted to energy when the two complete cities of Japan were destroyed back in 1949 due to that atomic bomb? It was 0.2 grams. 0.2 grams mass was converted to the energy. Only 0.2 grams. Due to this much of mass, the two cities were destroyed completely. You see the beauty of this universe. Are you able to understand, guys? Okay. There was a question asked on this in 2020. The energy equivalent to 0.5 gram of a substance is. You have to find the energy in the 0.5 gram of a substance. Okay. Find the energy in 0.5 gram of a substance. So directly you can use E is equal to mc square. What is the mass? Mass is given as 0.5 grams. Convert this to the kgs. Okay. Then put it over here and multiply, get the value of energy. Simple. Okay. Next. Okay, let's move on to this one. Let's move on to this one. Let's move on to this one. Nuclear size of nucleus. Okay, see, it has been verified experimentally. Volume of nucleus is directly proportional to the mass number. Like. You have got over here nucleus. Okay. And inside this nucleus, if I say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, we say we have to fit 10 nucleons. If you have to fit 10 nucleons in a nucleus, do you require bigger nucleus or smaller? Obviously bigger. Now you have 5 nucleons here. How many number of nucleon? So we say only 5 nucleons are present. So means it requires smaller nucleus to accommodate less number of nucleons. This requires bigger number of nucleus in order to accommodate 10 nucleons. So can I say volume of nucleus means size of nucleus is directly proportional to the mass number. And when it comes to the volume, how do we say volume? How do we say volume, guys? We say volume is 4 by 3 pi r cube. 4 by 3 pi r cube. It is directly proportional to the mass number, that is A. 4 by 3 pi is constant. We say r cube is proportional to A. So we can say r is proportional to A raised power 1 by 3, because if you take this over here, it will become 1 by 3. So radius is proportional to r raised power 1 by 3. R will be equals to r naught A raised power 1 by 3. Okay. And what is the value of R naught? R naught is 1 Fermi meter. 1 Fermi meter is 10 raised power minus 15 meters. So basically, this is the radius of the nucleus. This is how we define the radius of the nucleus. Then we say nuclear density. Nuclear density is simply density of the nucleus. Okay. Like you say radius of nucleus, density of nucleus. Density of nucleus, okay. Density of nucleus will be mass divided by volume. Mass of, directly. Density of nucleus is constant, that is 10 raised power 17 kg per meter cube. And it is constant for all nuclei. Density of nucleus is constant for all the nuclei. It is 10 raised power 17 kg per meter cube. Okay, let's take a look at this question. Radius of 2He4 nucleus is 3 Fermi meter. Okay. It says that radius of He, okay, this nucleus, helium nucleus, it is 3 Fermi meter. It is 3 Fermi meter. Okay. The radius of 16s32, we are supposed to find radius of this sulfur. Okay. Will be, guys, tell me one thing. How do we write this? We say, when it comes to the radius, it is proportional to a raised power 1 by 3. We say a radius of He divided by a radius of sulfur. It will be a mass number of He divided by mass number of S whole raised power 1 by 3. Now guys, here this means mass number, here this means mass number. So can I say, in this particular case, this is a radius of He. Radius of He is given as how much? That is 3 divided by radius of S we need to calculate. It will be equals to, that is mass number of helium, that is 4. Mass number of sulfur, that is 32 whole raised power 1 by 3. So this is 3 divided by radius of S will be equals to 4 ones are 4 eights are 1 by 8, its cube root, that is 2. 1 divided by 2, because 2 into 2 into 2 is 8. So now 3 into 2 is 6. Do the cross multiply. So radius of sulfur, it is going to be 6 Fermi meter. It is going to be 6 Fermi meter. Okay. Yes. Next. Okay. Let's talk about binding energy and mass defect. Binding energy and mass defect. Binding energy and mass defect. Guys, let's suppose we have a nucleus over here. We have a nucleus over here. And guys. Or before this, let me just, or directly I'll show. We have a nucleus over here. Okay. We say mass number of this nucleus is A. A means the number of nucleons. Okay. Z is the atomic number. Okay. Number of protons. Now, let's suppose collective mass of this nucleus is M. Collective mass of this nucleus is M. I am saying that break this nucleus. Okay. If you break this nucleus, you will have to use the energy. So when you break the nucleus, you are taking out the protons, you are taking out the neutrons. Guys, see, if Z is the atomic number, how many number of protons are there? Z, because Z is the atomic number. And what is the mass of one proton? That is MP. What is the mass of one proton? That is MP. What is the mass of one proton? That is MP. What is the mass of two protons? 2MP. What is the mass of Z protons? That is ZMP. Okay, this ZMP. So this will be ZMP. Then plus. If A is the total number of nucleons, Z is the protons, how many number of neutrons will be there? A minus Z. So here I'll write A minus Z, Mn. Mn is the mass of neutron. Okay. So this is greater than capital M. So capital M is the collective mass. What I'm trying to say is that when these nucleons were together inside the nucleus, their mass was capital M. When I took them out, I am placing these are the protons. I am placing these protons here. I'm placing these neutrons here. When I calculated their mass, it came out to be greater than that collective mass. Okay. Why is it like that? It is because the energy which is used in breaking the nucleus, this energy which we used in breaking the nucleus, is stored in the form of mass, of nucleons. So basically, guys, mass of protons and neutrons is inside something. When you break the nucleus, some energy is stored in the form of mass of these nucleons. So when you took them out, so that's the reason mass individually later on came out to be greater than this. Okay, okay, okay. And this energy which is used in breaking the nucleus, this is called a binding energy. This is called binding energy. And now, guys, don't you think that in this case mass defect has arisen? Why? Let's suppose later on initially mass was 10 kg. Finally also mass should be 10 kg, but finally mass is coming out to be 12. So how much is the defect? That is 12 minus 10, that is 2 kgs. That is 2 kgs. Okay, that is 2 kg. That is 2 kgs. Okay. Now, due to this only, mass defect has occurred. And if I say how much is the mass defect, that is delta M. That will be ZMP plus A minus ZMN minus M collective. So this is final mass. This is final mass. Mass finally. Okay. And this is mass initially. This is mass finally minus mass initially. Okay, mass finally minus mass initially. Now, guys, if somebody asks you what is the binding and how much is the binding energy over here, binding energy here will be delta M into C square. Guys, it is logical. If I'm saying due to this energy, mass has been stored. Let's suppose due to this binding energy, we said 10 kg mass has been stored. Now, if I am saying how much is this binding energy, you check how much is the energy in this 10 kg. That will be the binding energy. How do you find that? E is equal to mc square. Simple. So that's what I'm saying over here. Binding energy will be mass stored, that is mass defect, okay, into C square. Mass defect will be ZMP plus A minus ZMN minus M into C square. This is what we call the binding energy. This is what we call the binding energy. One more important thing, we say binding energy per nucleon is proportional to stability. Binding energy per nucleon is proportional to stability. See. What I'm trying to say is that, guys, what does binding energy per nucleon mean? Let's suppose this is the nucleus. You have got 6 nucleons inside the nucleus. Okay. If I am saying what is the binding, how do we define binding energy? Binding energy, we say total energy required to take out, to break the nucleus or to take out all the nucleons, to take out all the nucleons. Okay, to take out all the nucleons. So total energy required to take out all the nucleons, that is the total binding energy. When I define binding energy per nucleon means per mass number. So this means energy required to take out one nucleon from the nucleus. Okay, how much is the energy required in taking out one nucleon from the nucleus? That is called binding energy per nucleon. That is called binding energy per nucleon. And this binding energy per nucleon Okay, it is proportional to stability. It is proportional to stability. That means if you have a nucleus over here, and if let's suppose here binding energy per nucleon is 3 electron volts. If there is another nucleus, and here binding energy per nucleon is, let's suppose, 4 electron volts, means this nucleus is more stable than this. Why? Because here you need to apply more energy in taking out one electron. Here you need to apply less energy in taking out one electron. That's why we say this is more stable as compared to this. I have a question on this one also. That is this. This is the question. A nucleus of 4x6 and 6y12 having binding energy x and y are 24 electron volt and 36 electron volt. 24 electron volt and 36 electron volt. A nucleus of 4x6 and 6y12 having binding energy x and y are 24 and this. Which of the two nuclei is more stable? Which one is more stable? Which one is more stable? Which of the two nuclei is more stable? Guys, see, this X nuclei has binding energy, total binding energy. Guys, we say binding energy of X. It is given as 24 electron volts. If I ask you, how much is the binding energy per nucleon? Binding energy per nucleon means energy which is required in taking out one nucleon. So that will be total binding energy is 24 divided by how many nucleons are there in X? That is 6. So this will be 4 electron volt. Okay. Now, when it comes to the binding energy of Y, binding energy of Y is given as 36 electron volts. And if I write over here binding energy per nucleon in this particular case, so that will be 36 divided by per nucleon. How many nucleons are there? That is 12. So that is 3 electron volt. Now here binding energy per nucleon is less. Here binding energy per nucleon is more. So can I write in this particular case? So X is more stable than Y. 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 Now take a look, guys. Graph between binding energy per nucleon versus mass number. So basically, we have a graph that is between binding energy per nucleon versus mass number. Binding energy per nucleon versus mass number. Graph between binding energy per nucleon versus mass number. Guys, I want you guys to focus exactly over here. Listen. Experimentally, we have seen graph between binding energy per nucleon and mass number is something like this. Binding energy per nucleon, or you can write over here, this is stability. Because binding energy per nucleon or stability, it is one and the same thing. Now, experimentally, it has been seen. The graph varies something like this. See, guys, you see the nucleus which is, let's suppose, if there is a nucleus which has mass number A is equal to 30. If there is a nucleus which has mass number A is equal to not 30. If there is a nucleus which has mass number A is equal to 10, don't you think that it has got less binding energy per nucleon? means it has less stability. It is less stable, yes. Sir, this nucleus will also have less stability. This nucleus will also have less stability, yes. Now, if you check here, this nucleus has got a large stability. So means, all those nucleons which lie, here it is mentioned. We say those nucleons with mass number less than 30 are called lighter nuclei and are unstable. You see, these are the lighter nuclei. Mass number 30 is here. Less than 30, these are the lighter nuclei. Okay, they have less nucleons, so they are unstable. They are unstable. They are unstable. They are unstable. Those nuclei with mass number A is greater than 170 are called heavy nuclei and also unstable. See, binding energy per nucleon is increasing. From here to here, it remains large. Then again, it is decreasing. Then again, it is decreasing. So, those nucleons which has got binding energy greater than 170, they are also unstable. They are also unstable. Okay. Okay. So, my dear friends, all of those nucleons which lie between 30 and 170, those are stable. Those are highly stable because their stability curve is large, huge. Okay. Now, guys, we say two lighter nuclei will combine to form a bigger nuclei in order to achieve stability. See? Now, this nuclei is lighter. This is lighter. They combine together. When they combine together, why? So that they achieve stability. So that, now let's suppose, guys, this is, let's suppose 15. This is 16. 16 plus 15 is 31. Now it is in this range. So basically, when two nuclei combine together, fuse together to form a bigger nuclei to achieve stability, this process is called fusion. This process is called fusion. Two lighter nuclei will combine together to form a bigger nuclei in order to achieve stability, and this process is called fusion. And we say energy is released in this process. Energy is released in this process. Okay, energy is released in this process because whenever something moves towards stability, whenever something achieves stability, energy is released in that process. Energy is released in that process. Okay. Also, a bigger nuclei with mass number less than 170. Also, a bigger nuclei with mass number less than 170 breaks into two smaller nuclei to gain stability. This process is called fission. Like, you have a bigger nuclei over here. It is unstable. It will break into two smaller nuclei to achieve stability. Like, its mass number is 200. It will break into 100. So that is stable. So we say this process is called a fission. And in this process also energy is released. Why? Because whenever something achieves stability, energy is released in that case. Okay. Then, guys, you have Q value of the reaction. Okay. What does Q value of the reaction actually mean? This is how much energy is released or absorbed. Q value of the reaction simply means how much energy is released or absorbed. Like, let's suppose you have two nuclei, A nuclei plus B nuclei. These are called reactant nuclei. If these two nuclei are converted to C plus D, if these two nuclei are converted to C plus D, okay, so reactant nuclei is converted to product nuclei. A plus B is converted to C plus D. Then we say over here plus Q. Q means Q value of the reaction. Q means Q value of the reaction. Okay. So react like in case of fission, two nuclei combine together to form another nuclei, bigger nuclei. Similarly, two nuclei are converted to C plus D. A plus B is converted to C plus D. During this reaction, we say some energy may be either absorbed. During this nuclear reaction, some energy may be either absorbed or released. This is called Q value of the reaction. And if you have to find how much energy is absorbed or released, you say you say this Q value of the reaction will be mass of reactants minus mass of products multiplied by C square. Mass of reactants minus mass of products multiplied by C square. When it comes to the mass of reactants, that is mass of A plus mass of B. Mass of reactants means mass of A plus mass of B minus mass of C plus mass of D minus mass of C plus mass of D into C square. Guys, Q value of the reaction can be calculated mass of A plus mass of B, mass of A plus mass of B minus mass of C plus mass of D into C square. Okay. Okay. Now guys, see. If mass of A plus mass of B is greater than mass of C plus mass of D, in that case, Q value will come out to be positive. It is like, if let's suppose this is 10, this is 5. 10 minus 5 is plus 5. In that case, Q value is positive. That means energy is released. That means it's an exothermic process. Okay. Now, if mass of A plus mass of B is less than mass of C plus mass of D, mass of reactants is less than mass of products, like if I am saying this is 5 and that is 10, 5 minus 10 is minus 5. In that case, Q will come out to be negative. Q is negative, that means energy is absorbed. Energy is absorbed means it's an endothermic process. Like, this is important. To write Q value of the reaction in terms of binding energy. Now guys, this Q value of the reaction in terms of binding energy is binding energy of C or plus binding energy of D minus binding energy of A plus binding energy of B. I can write it like this. This is binding energy of products, okay, minus binding energy of reactants. As simple as that. In terms, this is the Q value of the reaction in terms of binding energy. This equation will be mostly using in solving the questions. Okay. Before this, let's talk about this one. Guys, in a nuclear fusion reaction, tell me one thing. If the energy is released, then binding energy of products is equal to binding energy of reactants greater C. Nuclear fusion reaction, we say in nuclear fusion. In nuclear fusion, we say energy is released. Energy is released. What does that mean? That means Q is positive. If Q is positive, Q will only come out to be positive. Take a look. If binding energy of products is greater than binding energy of reactants, 10 minus 5 is plus 5. Q will only come out to be positive if binding energy of products is greater than binding energy of reactants. Else Q will not be positive. So, option C. Let's take a look at this question. Guys, take a look. The binding energy per nucleon of 3Li7. The binding energy per nucleon of 3Li7 and 2He4 are binding energy per nucleon of 3Li7, 2He4 are 5.60 and 7.06 respectively. In the nuclear reaction, this is the nuclear reaction. That is 3Li7 plus 1H1. It is not 1He1, it is 1H1. It gives 2He4, 2 helium nuclei plus 2He4 plus Q. We are supposed to find the value of Q value of the reaction. Guys, simply Q value of the reaction is binding energy of products minus binding energy of reactants. That's it. Let me show you. See, binding energy per nucleon of 3Li7 means binding energy of one nucleon for 3Li7 is how much? 5.60. Means if you have to take out one nucleon from this 3Li7 nucleus, you have to use this much of energy. In order to take all 7 out, how much energy is required? 7 into 5.60. Yes. So binding energy of product is 2He4. See. Binding energy per nucleon of 2He4 is 7.60. Means one nucleon of 2He4 has this much energy. So how many nucleons are there? This is 2He4. 4 plus 4 is 8. 8 nucleons are there in the product. So 8 nucleons will have how much binding energy? 8 into 7.06. So this will be 8 into 7.06. Then we say minus. Binding energy of reactants. Reactant is this 1H1. Leave it. It is only 1H1 means proton. 1H1 means proton. Now 3Li7. Binding energy per nucleon. Binding energy of one nucleon of 3Li7 is 5.60. How many nucleons are there? 7. So 7 nucleons will have how much binding energy? 7 into, 7 into, we say 5.60. So one has this much, 8 will have 8 into this much. One has this much, 7 will have 7 into this much. Okay, now find the answer. Okay, now find the answer in this particular case. 39.2, 39.2 MeV. That's it. Next one. Take a look. Guys, we have got two more slides and then we are starting the next chapter. So I think we must finish this chapter in next 10 minutes. Then we should take the break. What do you guys think? I think we should finish these 2 slides, this chapter. Then we should take the break. What do you guys think? Tell me. What do you guys think? Yes, let's do that only 10 more minutes. See, let's take a look at this question first. See, the binding energy per nucleon for a deuteron and an alpha particle are X1 and X2 respectively. What is the Q value of the reaction in this? See. We have got 1H2. This is the reaction. 1H2 plus 1H2 gives 2He4 plus we say Q. Okay, guys, binding energy per nucleon of deuteron means 1H2, alpha particle is 2He4. We have to find Q. Q value of the reaction will be simply binding energy of products minus binding energy of reactants. Now see, Q will be binding energy of product. Product is what? 2He4. Binding energy per nucleon of one nucleon of alpha particle has how much binding energy? X2. So 4 will have how much? 4 into X2. So this will be 4 into X2, then minus binding energy per nucleon of deuteron. Okay, deuteron is 1H2. It is X1. So how many nucleons are there? 2 plus 2 is 4. So 4 nucleons will have how much binding energy? 4 into X1. So here you can say 4X2 minus X1. This is the Q value of the reaction. This is the Q value of the reaction. Now guys, take a look. Nuclear force. When it comes to the nuclear force, we say it acts between the nucleons. It acts between the nucleons. Okay. So this nuclear force between 2 protons will be equals to nuclear force between 2 neutrons will be equal to nuclear force between neutron and a proton. Will be equals to the nuclear force between neutron and a proton. Okay. 2 protons, 2 neutrons. 2 protons, 2 neutrons, a proton and a neutron. Okay. So my dear friends, listen to me very carefully. Listen to me. Inside the nucleus, you have large number of nucleons, okay? So let's suppose you take this proton and this proton. We say this proton will repel this proton will repel this proton with what force? Electrostatic force. Okay. And this electrostatic force will be extremely huge. Why? Because distance between these two is extremely small, so force will be extremely large. Now these two protons are trying to break the nucleus, wants to come out. Then we say they are together, then nuclear force acts. Because of the nuclear force, they stay together. I hope you got the feel. So due to the electrostatic force, they want to break the walls of the nucleus. But due to the nuclear force, they stay together inside the nucleus. Okay. Okay. So I'll write due to F electrostatic, nucleons, we say protons wants to break the walls of the nucleus. Protons wants to break the walls of the nucleus. But due to electrostatic force, but due to nuclear force, they stay together. Okay? They stay together. Now, my dear friends, when it comes to this nuclear force, it is 100 times greater than electrostatic force. When it comes to this nuclear force, it is 10 raised power 39 times greater than gravitational force. 10 raised power 39 times greater than gravitational force. Okay? Yes. Now, my dear friends, listen to me very carefully. Graph between the potential energy versus distance between the nucleons. Graph between the potential energy and distance between the nucleons. I want you to understand this graph. It is very important. See, so we say U, or we say potential energy versus, U versus R. Guys, in the electrostatics, we have studied if we have a charge Q1, if we have a charge Q2, distance between the two charges R. We say the force between them is K, Q1, Q2 divided by R square. Okay. This is the force between the two charges. Now, similarly, we have studied potential energy between the two charges, that is K, Q1, Q2 divided by R. This is the potential energy between the two charges. Now, potential energy and R has inverse relation over here. Similarly, if you have two nucleons, let's suppose proton, this is neutron. Sir, here also between them potential energy will exist. Now, this is the distance between the two nucleons. Now, what is the graph of potential energy versus R in case of the nucleons? That is something like this. Okay. Experimentally, it has been seen, it is something like this. Let's suppose this is point A. You consider this as point A. This is point B. And here, this is point C. I would want you guys to understand. I would want you guys to focus over here. Okay, take a look. Guys, if I say, listen to me very carefully. If I say, this is a line over here. What is this angle? This is less than 90. So always remember, if theta is less than 90, slope of that graph is positive. If I say, sir, what about this one? Here, theta is greater than 90, less than 180. In this case, always remember, slope will be negative. So this is the decreasing graph. Its slope is negative. This is increasing. Its slope is positive. Now take a look. We say from A to B. Guys, we say from A to B. I would want you guys to focus. We say slope is positive from A to B. Sorry, slope is negative. Why? Because if you take a line over here, that is making the angle greater than 90 degrees. Slope is negative. And when it comes to slope, guys, if I say this is y versus x, slope will be here, dy divided by dx in case of y versus x graph. And here, my dear friends, when it comes to the slope will be, that is du divided by dr. Slope will be du divided by dr. Take a look. One formula I just want to say. There is a formula as we know. Relation between potential energy and force. Say F is equal to minus du divided by dr. I want you guys to remember this directly. So this is the relation between force and potential energy, du by dr. Now here slope is du by dr, and we know force is minus du divided by dr. Now from this equation and this equation, can I say force will be equal to the negative of slope? So force will be negative of slope. Yes. Now guys, tell me one thing. From A to B, slope is negative. So you'll be saying, sir, force will be negative of negative. So we say F is equal to will be positive. What is this actually? See guys. We say exactly. This will be the point where value of R is 0.5 Fermi meter. So this A to B graph, this portion of the graph, it lies on the left side of 0.5 Fermi meter. Means this is the graph of potential energy between the nucleons when their separation is less than 0.5 Fermi meter from A to B. Guys, I'll write over here when R is less than 0.5 Fermi meter. In that case, we say slope is negative. In that case, we say force is positive. In that case, my dear friends, force is positive means force is repulsive. See, I'll make you understand this particular point. Let's suppose this is a nucleon, this is proton, this is neutron. I want you to understand this. We say these two nucleons are attracting with a nuclear force. This is a huge force. Now, due to this huge force, they come together. If the distance becomes less than 0.5 Fermi meter, okay, now they start repelling. Again, they start repelling. Why? Because if they keep on attracting, the time will come, they will collapse. So that is the reason, if the distance between them becomes less than 0.5, so they start repelling each other. That's why we say force becomes repulsive when R is less than 0.5 Fermi meter. And similarly, guys, take a look. From B to C, we say value of R is 0.5 Fermi meter. Okay. So I can say, guys, what is the value of slope? Slope is positive. Okay. And when it comes to the force, that is negative of slope. Recently we saw force is negative of slope. So force will be minus. Negative of slope, this will be positive. Slope is positive from B to C. So force will come out to be negative. Negative will be attractive. So negative will be attractive. So my dear friends, negative will be attractive. So we say if distance between the nucleon becomes greater than 0.5 Fermi meter, in that case force becomes attractive. Okay, so this was the complete detail about this one. So next chapter we will be starting, that is semiconductors. Okay. And guys, we say break. This is the next chapter. next chapter, and I would say break till 11 p.m. Yes, break is till 11. Go get done with your dinner. Okay, guys, we're back. So let's start with the new chapter, that is semiconductors. Take a look, guys. When it comes to the materials that we have seen as of now, that we have studied till now, we have studied about the conductors. We have studied about the insulators. We say conductors are those materials in which conduction is possible. Okay. In which there are large number of free electrons. Okay. Conductors are those materials in which there are large number of free electrons. That's why conduction is possible, because whenever free electrons move in a conductor, then only current is produced. When it comes to the insulator, we say conduction is not possible in an insulator. Current cannot flow in an insulator. Why? Because there are no free electrons in an insulator. And when it comes to the semiconductor, we say it is that material which lies between the conductor and insulator. It is that material which lies between the conductor and insulator. Okay? It has dual nature, means it can behave like a conductor, it can behave like an insulator. That's why we say it's a special material. Its conductivity and resistivity can be controlled. Like guys, when it comes to conductor, semiconductor, insulator, conductivity of semiconductor is between 10 raised power 2 to 10 raised power 8 ohm meter inverse. Then you have got for semiconductor, we say its conductivity is between 10 raised power minus 2 to 10 raised power 6 ohm meter inverse. Then you have got insulator. We say its conductivity is less than 10 raised power minus 6 ohm meter inverse. Guys, if you decrease the conductivity of the semiconductor, it will behave like an insulator. If you increase the conductivity, make it 10 raised power 6, it will behave like a conductor. That's why we say it's a special material. It can behave like an insulator, it can behave like a conductor. Now the important topic, that is a band diagram. Guys, listen. We say, let's suppose we have a material or a crystal. I'm taking a material over here. Okay, this is any material. We know that in this material, there are millions of atoms. Like if I say this pen is made up of millions of atoms. And in those millions of atoms, it has got millions of electrons. Okay. And these electrons are present in the energy levels, which forms the energy band. So these materials, these electrons, my dear friends, in a material, they are present in energy levels like this. This is the energy level. In every energy level, there are 2 electrons. Okay. This as a whole is what we call the energy band diagram. So if this is a material, in this material, there are millions of atoms. Now in these millions of atoms, there are millions of electrons. Those electrons are present like this in the energy bands, This is how we define it over here. This is how we define it over here. Okay. Okay. Yes. Now guys, we have band diagram in case of semiconductors. We have band diagram in case of conductors. We have band diagram in case of insulators. Let's talk about band diagram of semiconductors. See guys, I have got over here band diagram of semiconductors. We say, see, this band which is from the upper side, this is what we call conduction band. This is what we call conduction band. Okay. And we say in conduction band, electrons are present. Those electrons are called free electrons. Okay. And from this lower side, this band is called valence band. When we see the band diagram of a semiconductor, it looks like this. Upper portion is called conduction band, lower portion is called valence band. And this is the energy band gap. Okay. And my dear friends, we say this one is the highest maximum energy level of valence band, or we say EV maximum. And this is the minimum energy level of conduction band. Now see, at 0 Kelvin, conduction band is completely empty and valence band is completely filled. Guys, we say this valence band is filled with these electrons are called, we say fixed electrons. Okay? Or we say bonded electrons, bonded electrons. Bonded electrons. So the electrons present in this are bonded, and the electrons present in this are free electrons. Free electrons. Okay. So we say in this particular case at 0 Kelvin, 0 Kelvin means you have not increased the temperature of a semiconductor. We say this conduction band is completely filled, valence band is completely empty. Valence band is completely empty. Okay. Now guys, if we increase the temperature, at T is equal to 300 Kelvin, we say bonded electrons will move to the conduction band. Let's suppose now you have increased the temperature. So we say these bonded electrons will shift to the conduction band. These will shift to the conduction band. These will shift to the conduction band. Keep this thing in your mind. Okay. Now guys, listen. We say when these electrons shift to the conduction band, in that case, we say hole will be created over here. Because electrons will leave this position, now hole will be created. So, electrons will leave this position and hole will be created. Hole will be created. Okay, yes. So, this is how does and one more important thing, guys. At T is equal to 300 Kelvin, we say this becomes partially filled, this becomes partially empty. Yeah. Next, let's make the band diagram for conductors. Guys, if you see the band diagram of conductors over here, we say it is this conduction band is overlapping with the valence band. There is no energy band gap. And in this particular case, we say at 0 Kelvin, conduction band as well as valence band is completely filled. But in case of semiconductors, conduction band is completely empty at 0 Kelvin and valence band is completely filled at 0 Kelvin. So when you increase the temperature, these electrons shift from valence band to the conduction band. Valence band to the conduction band. Okay. And when it comes to the band diagram of insulators, you take a look here. Guys, band diagram of insulators, you take a look. In this particular case, this is conduction band and this one is valence band. This is the energy band gap. This is the energy band gap. And we say this energy band gap is greater or equal to 3 electron volts. And guys, here, when it comes to the insulator, we say at T is equal to 0 Kelvin, this conduction valence band is completely filled and conduction band is completely empty. Even if you increase the temperature, we say this band gap is so large, these electrons won't be able to reach over here. That's why in case of insulator, we say no free electrons. No free electrons. Free electrons will be present in the conduction band. So conduction band is completely empty if you increase the temperature. So no current will exactly flow over here. So basically, when you take a look at the band diagram of semiconductors once again, so it is simply this band is completely empty at 0 Kelvin. This is completely filled. When you increase the temperature, we say these electrons will shift over here. Now take a look over here in this case. Two types of semiconductors. Guys, there are two types of semiconductors. First one is, we say intrinsic, okay, or you can call it the pure semiconductor. Pure semiconductor. Second one is called the extrinsic, that is impure semiconductor. Impure semiconductor. Now guys, let's take a look here. In this particular case, let's talk about conduction in case of pure semiconductors. Guys, let's suppose you are taking a semiconductor over here. Since when you increase the temperature, electrons will shift from valence band to the conduction band. Okay, so holes are created in the valence band. So we say, let's suppose this is a semiconductor, already some holes are created. This is the hole which is already created. Already some holes are created. And these are the electrons. These are the electrons. Now this is the positive terminal. This is the negative terminal. Okay. Now electric field is set up from positive to negative. Electric field is set up from positive to negative. This is the electric field which is set up from positive to negative. Now guys, let's suppose I am taking a pure semiconductor. Let's take a pure silicon. Let's take a pure silicon. And pure silicon means pure semiconductor. In this already a hole is there, electrons are there. Okay, free electrons in the conduction band and holes in the valence band. Now guys, if you apply the electric field over here, means this battery, you are applying electric field. Don't you think that, sir, on this electron, force will act in the opposite direction, so it will go and it will be occupied in the hole? Now it looks like hole is moving towards, electron is moving towards left, hole is moving towards right. Why? Because when this electron moves from this point to this point, it will be occupied here. Now hole will be created here. Now, in this case, we say here holes as well as electrons both move. Here holes as well as electrons both move. So current is produced. Okay. So in this particular case, current will be due to holes as well as electrons. And current I is due to, why? Because hole has got positive charge. Guys, if I say there is an electron was present at this point, electron is leaving this point. Now what will occupy at this point? Positive charge. Positive charge is basically deficiency of electrons. So I is due to holes and electrons. I is due to holes as well as electrons. So this net current, if you see in a conductor, in a pure semiconductor, it is Ni. Okay. And then we say E charge on an electron area, delta V potential difference, mu E. Mu E is the mobility of electrons plus mobility of holes. Okay. Ni is the intrinsic charge carrier density. Okay. Or this is not that Ni, sorry. This is NiAVD. N is the number of free electrons per unit volume. Okay. I is the charge on current. Okay. And IAVD. Okay. Now guys, let's move on to the next one over here. Let's move on to the next one over here. Then you have the extrinsic semiconductor. Guys, when you define the extrinsic semiconductor, there are two types of extrinsic semiconductors. First one is N-type and second one is P-type. First one is N-type and second one is P-type. Now, why do we basically create extrinsic semiconductors, impure semiconductors? Guys, We make an impure semiconductor because we want to increase its conductivity. That's why we want to increase its conductivity. See. So when it comes to the impure semiconductor, first impure semiconductor is N-type. How do we create the N-type? Let's take a pure silicon. This is the pure silicon. And silicon has got 4 valence electrons. These are the valence electrons. Okay? Okay, yes. Now, in this case, we are adding phosphorus. Okay, phosphorus. We are adding phosphorus. And basically, my dear friends, if you have a silicon crystal, we say add the phosphorus impurity. Add the phosphorus impurity to this one. Okay. So in this case, phosphorus, we say it is a pentavalent impurity. Pentavalent impurity. We say phosphorus is a pentavalent impurity. We say phosphorus is a pentavalent impurity. Now, my dear friends, I am saying pentavalent impurity means which has got 5 valence electrons. Here, in order to fit into this crystal, phosphorus must have 4 only, but it has 5. So what will the phosphorus do? Okay. Phosphorus will lose 1 electron, minus 1 electron, and it will become phosphorus positive. That is positive donor ion. It will be called as positive donor ion. So phosphorus will basically lose 1 electron. It will become phosphorus positive. That is positive donor ion. That is positive donor ion. So my dear friends, if you take a look over here, this one is the pure silicon. Once you add the phosphorus is added over here. Now phosphorus will create the bond over here, okay, with the 4 valence electrons, and one it is donating, that is this free electron. Now if I'm saying on adding millions of phosphorus, I'll write over here, on adding millions of phosphorus. We say millions of electrons are donated. Millions of electrons are donated. Okay. So if millions of electrons are donated, so conductivity increases. Conductivity increases. So conductivity increases, as simple as that. Now take a look, guys. Here. Now guys, in this particular case, if I ask you, on adding the phosphorus, we say electrons are donated. Can I say in this particular case, majority charge carriers, in this case we say, in this particular case, we say electrons will be the majority charge carriers. Okay. Means number of electrons will be the majority charge carriers. Number of holes will be the minority charge carriers. Number of electrons will be the majority charge carriers. Number of holes will be the minority charge carriers. Okay. Majority charge carriers and minority charge carriers. And in this case, current due to electrons will be greater than current due to holes over here. Because we say mobility of electrons is greater than mobility of holes. Because mobility means if electrons have less mass, its mobility is more. And number of electrons will be equal to the number of donor ions. Means if you are adding 5 phosphorus, we say 5 electrons are donated. So that's why if you are adding million phosphorus, million electrons are donated. So here majority charge carriers are electrons. Why? Because you are adding phosphorus, that is releasing electron. So that's why that is majority charge carriers. This is minority charge carriers. Okay. And one more important thing, if somebody asks you, what will be the net charge of the N-type semiconductor? You always say net charge will be 0. Why? Because if you are adding 5 phosphorus, phosphorus has positive charge. We say 5 electrons are donated, 5 positive charge, 5 negative charge, net is 0. P-type semiconductor. Let's take a pure germanium. If you have to make the P-type semiconductor, what you are supposed to do? We say add boron impurity. And boron means trivalent impurity. Trivalent impurity. Guys, trivalent impurity means which has 3 valence electrons. In order to fit into this crystal, it must have 4. So when you add boron over here, guys, when you add boron over here, we say it will have only 3 valence electrons. Already germanium is present over there. Germanium is present. Okay, germanium has got its 4 valence electrons. Germanium has got its 4 valence electrons. Okay, so germanium will give its valence electron to this, okay, 4th one, and a hole is created. Okay, so 1 electron is added. It will gain 1 electron. It will become boron negative. That is negative acceptor ion. That is negative acceptor ion. So basically, if you have a pure semiconductor, this is a germanium crystal. In this germanium crystal, my dear friends, we say when you are adding boron has only 3 valence electrons. In order to fit into the crystal, it must have 4. So a germanium will give the electron to him, to boron. So a hole is created over here. Now, can I say on adding millions of boron, millions of holes will be created? So in this particular case, we say majority charge carriers will be holes. Because when you add boron, we say hole is created. So majority charge carriers will be holes in this particular case. And minority charge carriers is going to be the electrons in this particular case. Minority charge carriers is going to be electrons. And here, number of holes is much greater than number of electrons in this case. Okay. Okay. Yes. Because this is majority. And number of acceptor ions will be number of holes. Obviously, if you are adding 5 boron, that is the negative acceptor ion, we say 5 holes are created. If you are adding 10 boron, we say 10 holes are created. As simple as that. In an extrinsic semiconductor doped with pentavalent impurity. Extrinsic semiconductor doped with pentavalent impurity. Yes. And an intrinsic semiconductor, number of holes are same. Extrinsic semiconductor is which one? N-type. N-type. Okay. In case of see. Guys. I'm saying you have an extrinsic semiconductor, that is N-type semiconductor. Okay. We say in case of N-type semiconductor and a pure semiconductor, N-type and pure. Okay. So pure N-type means, and pure means in which there is no impurity. Let's suppose pure semiconductor has 5 holes. It has 5 holes already. In case of N-type semiconductor means you have added pentavalent impurity. We say here also, let's suppose initially it was 5 holes. So when you are adding impurity, my dear friends, when you are adding impurity, impurity is pentavalent. So we say electrons will increase, but holes will be there only 5. So holes will be 5 only. Electrons will keep on increasing. So we say in an extrinsic semiconductor doped with pentavalent impurity and an intrinsic semiconductor, number of holes are same. Assertion is correct. Number of holes doesn't depend upon doping concentration. Okay. Number of holes does not depend upon doping concentration. Number of holes does depend upon doping concentration. Okay. But Number of holes does depend upon doping concentration. So we say, like in semiconductors, in p-type semiconductor. So we say, if you are adding, we say impurity means you are doing doping. We say number of holes increases. So it is option C. Assertion is correct, reason is wrong. Take a look. Conductivity of a semiconductor increases on doping. Doping means adding impurity. When you add impurity, number of electrons increase. When number of electrons increase means conductivity increases. Yes, assertion is correct. Doping raises the temperature of a semiconductor. There is nothing there is no relation between doping and increase in temperature. Okay, so option C. Assertion is correct, reason is wrong. So option C. For the given applied voltage, current in N-type semiconductor is more than that in P-type semiconductor. Yes, yes. Why? Because in N-type semiconductor, majority charge carriers are electrons. In N-type semiconductor, majority charge carriers are electrons. Okay. And mobility of electrons is much greater than mobility of holes. So current due to electrons is much greater than current due to holes. So assertion is correct. Reason is mobility of electrons is greater than mobility of holes. Reason is correct. So option A. Assertion is correct. Reason is correct. And reason is the correct explanation of assertion. Neet 2019. Which of the statement is true for P-type semiconductor? In case of P-type semiconductor, holes are majority charge carriers, electrons are minority charge carriers. We say holes are majority charge carriers, trivalent atoms are the dopants. Yes, when it comes to the P-type semiconductor, you add boron. Okay, so on adding boron, holes are created. So boron is a trivalent impurity. Boron is a trivalent impurity. Okay. And majority charge holes are majority charge carriers. B. In an N-type semiconductor, which of the following statement is true? Holes are majority carriers, trivalent atoms are the dopants. It is for N-type semiconductor. Holes are majority, wrong. Electrons are majority carriers and trivalent atoms are dopants, wrong. Electrons are minority charge carriers, wrong. Holes are minority charge carriers and pentavalent atoms are dopants, yes. D. Okay. Guys, just give me a second. I'll come back. Just a second. Let's move on to the PN junction diode. See guys, when it comes to the PN junction diode, you have got a P-type semiconductor, you have got an N-type semiconductor, okay? PN junction diode means when P-type and N-type semiconductor are joined together. Guys, see, you have got, when it comes to the P-type semiconductor, it has got holes and majority charge carriers, okay? Okay. Okay, and these are the negative fixed ions. Means this is that negative phosphorus, sorry, negative boron, negative boron, negative boron, which are fixed. Okay. Okay, and this is the majority, holes. When it comes to the n-type semiconductors, we know electrons are majority charge carriers. Okay, this is majority. And this is phosphorus positive, phosphorus positive, phosphorus positive. When you join them together, so we say whenever these electrons see the holes, they recombine. Electrons will go into the holes, okay, and the depletion region is formed. Now, if electrons move into the holes, now here hole will be created. So positive charge, positive charge. So on this line, it will be positive charge. So on this line, it will be negative charge. So it is negative charge, positive charge. So electric field is set up from positive charge to negative charge. This region is called depletion region. Okay. Now, guys, in this case, we say current is produced. We say when electrons move from N to P, in that case, current will be produced. That is called diffusion current. I diffusion is produced due to the recombination of electrons and holes. When electrons and holes recombine, a current is produced. That's called diffusion current. And drift current is produced due to the electric field in the depletion region, which makes the minority to move. Guys, when electrons shift here, due to that, diffusion current is produced. When it comes to the drift current, we say here, electric field is set up and the minority charge carriers will be here. Like in case of p-type, those are electrons. In case of n-type, those are holes. We say those electrons and holes will experience the force. Current is being produced there also. Okay. Then we say at some time, this diffusion current will be equal to the drift current and net current will be zero. Net current will be zero. This diffusion current will be from P to N. This will be from N to P, and net current in this is zero. So basically, in case of PN junction diode, we say net current is zero. Now, let's do the forward biasing of PN junction diode. Let's do the forward biasing of PN junction diode. Let's do the forward biasing of PN junction diode. See, guys, you have a semiconductor over here. This is the semiconductor that you are having. Okay. And this semiconductor, this has got the P side, this has got N side, this is the depletion region. This is the electric field in the depletion region. Now, what does forward bias mean? Forward bias means when connect a battery, when positive terminal of the battery is connected to P side, negative terminal of the battery is connected to N side. This diode is said to be forward biased. Now, guys, see. We say, now when the depletion region decreases, the electrons from N and holes from P start recombining. See, guys, when you basically connect this positive terminal to this, so this positive terminal will kind of send positive charge over here. Now, this positive charge will repel these holes. This positive charge will repel these holes. And this negative charge will accumulate over here. This negative charge will repel these electrons due to the forward biasing. Now, depletion region will decrease, due to which depletion region will decrease. Again, electron-hole recombine takes place. Electron-hole recombination take place. Okay. Now, my dear friends, when depletion region decreases and electron-hole recombination takes place once again, so I can say, now these electrons will not stop here. They will flow through the battery. These electrons will flow through the battery. Okay. Once again, they reach over here. Once again, depletion region will decrease. They'll go over here. This is the procedure of forward current, or this is the procedure of current in case of forward bias. Okay. Battery will make these electrons to flow to the N side once again. Okay. Now, if somebody asks you what is the graph of current versus voltage in case of forward bias, this will be the graph. This one. Okay. When initially there is less potential, current is less. at this large potential, current is huge. Okay. And when I say the symbol of forward bias, the symbol of forward bias is this one. The symbol of forward bias is this. This is the symbol of forward bias. This is the symbol of forward bias. Okay. And this is the P side is the back side, N side is the forward side. Okay. P side and N side. Okay. Yes. Okay. And in this particular case, we say in case of forward bias, this diode behaves like a simple wire. Current can easily flow. In case of forward bias, we say current can easily flow. Okay. Then we say reverse bias. Reverse bias means when positive terminal is connected to P side, negative terminal is connected to N side. Now see, in this case, it will send the positive charge here. But it is negative terminal, it will send the negative charge here. It will send the positive charge over here. Now this negative charge will attract these holes. This positive charge will attract these electrons. Depletion region increases. In this case, depletion region increases. So if depletion region increases, electron hole recombination will not take place. If electron hole recombination does not take place, current cannot flow in this one. So we say in case of reverse bias, the graph of current would be something like this. Okay. And this current is almost zero here. No doubt it is increasing. It is increasing after some time. See why it is increasing. We say as you keep on increasing the external electric field, in this depletion region, electric field will increase by large amounts. Due to that, bonds will break here. Okay, then charge flows. So when the charge flow, that current will be this. But when you compare this current with the forward current, it is very small, very small. Okay, and the point or the voltage. Okay, as you keep on increasing the voltage, the point where the value of potential difference voltage where bonds will break, that is called breakdown voltage. That is called breakdown voltage. It is mentioned over here. That is called breakdown voltage. That is called a breakdown. And in case of reverse bias, this negative terminal is connected to P side, positive terminal is connected to N side. Here in this particular case, current cannot flow because a reverse bias diode behaves like an open wire. It behaves like an open wire. Tell me in the chats, is this clear? Is this clear? Guys, is this clear? Tell me. Okay, that's great. Let's move on to the next one. So basically, when it comes to the forward bias, this is the current flow in case of forward bias. Current is in the large amounts. And this is the potential which is called the barrier potential. Okay. So this is called the barrier potential. At barrier potential, Current in the forward bias is very large, okay? Current in the forward bias is very large. Okay. And when it comes to the reverse bias, we almost say current flow is zero. There is no current in the reverse bias. No doubt you can see the current in the graph here, but compared to the forward current, it is very small. It is almost zero. In a PN junction diode, guys, see, in an unbiased PN junction diode, holes diffuse from P region to N region. In an unbiased PN junction diode, holes diffuse from P region to N region. Yes, because holes have got the majority charge carriers, and P-type has got the majority charge carriers when it comes to the holes. Yes. Hole concentration in P region is more as compared to the N region. Yes, assertion is correct. Reason is correct. Reason is the correct explanation of assertion. Okay. Neet 2020. The increase in the width of the depletion region in PN junction diode is due to the increase in the width is due to the reverse bias only. Is due to the reverse bias only. Recently we saw it. Which of the following diode is forward biased? Guys. How do we see forward biased? This is P side, this is N side. Now, P side is connected to higher potential, N side is connected to lower potential. This is positive, this is negative. Okay. Now guys, in this particular case, this is here. This is P side, this is N side. P side is connected to higher potential. Okay. N side is connected to lower potential. Okay, sorry. It is 3 volt and here it is higher potential because 5 volt and it is lower potential. So what is this, guys? This means higher potential. This means lower potential. So if P side is connected to lower potential, so means this is reverse bias. Now here, this is P side, this is N side. P side is connected to 0, N side is connected to -2, means P side is higher. So this will be forward bias. And in this case, P side, this is N side, P side is connected to lower potential. N side is connected to higher potential. This is reverse bias. Okay. Because here it is -4. This is Pn. And in this case, N side is connected to +2. So this is higher potential from N side. This is lower potential from P side. This is again reverse bias. This was asked in NEET 2017. Two ideal diodes are connected as shown in the battery. Okay. The current supplied by the battery is, you guys are supposed to tell me what is the current supplied by the battery. Guys. If you check this diode D2, this diode D2 is reverse biased. This diode D2 is reverse biased. If you check diode D2, it is reverse biased over here. Okay. This diode D2 is reverse biased. This diode D2 is reverse biased. Why? Because this is N side, this is N side, this N side, and this is P side. N side is connected to higher potential. P side is connected to lower potential. So current in this is reverse bias. So current in this will be 0. Now current will be simply, that is, guys. What is that is V divided by R. V is how much? That is 5. And resistance you have to take this only. That is 5 by 10. That is 0.5 ampere. From the following diodes, which is the forward bias condition? So this is higher potential. This is lower potential. So this is higher. This is forward bias. Okay. And what about this one? Guys, this is reverse bias. Because this is N side, this is P side. N side is connected to 2, P side is connected to 0. Here, this is also reverse bias. Because P side is connected to -5, N side is connected to -2. This is also reverse bias. Okay, because N side is connected to 12, P side is connected to 5. Neet 2016. Neet 2016. The current in the resistance R1. We have to find the current in this resistance. Guys, see, this is higher potential, this is lower. In this particular case, this is N side, this is P side. Don't you think that here, N side is connected to higher potential, so this will be reverse bias. No current will flow through this. Now here, current, I can simply say V divided by R. Okay. You have to find the current in this one. Now this circuit will look something like this. So this is the battery, that is 10 volt. Then you have this resistance, that is 2 ohm. You have this resistance, that is 2 ohm. This is 2, this is 2 plus 2 is 4. Current will be V by R. V is 10, R is 2 plus 2 is 4. 10 by 4, that is 2.5. You have to check basically which one is forward bias and which one is reverse bias. In this particular case, you can clearly see, this diode is reverse biased. This is forward bias. So current will be simply V by R. V is, see guys. Here potential will divide. This is 5 volt. So 0.3 volt this is taking. So 5 minus 0.3, that is 4.7. 4.7 volts will go in this one. Now tell me what is the current? That is V by R. V is 4.7 divided by 10. This will be the current. Let's first move on to this one. Yeah, Zener Diode. This is important. Is this clear till over here? Tell me. Quickly, guys, tell me. Now we need to study Zener Diode. Is this clear? Give me the signal in the chats, guys. Give me the signal in the chats. Is this clear? Everyone, tell me, is this clear? Everyone means everyone. Tell me, guys. And if you have not liked this session yet, I would want you guys to smash the like button. That's great. That's great. That's great. Amazing. Now let's start the Zener diode. Let's start the Zener diode. Take a look, guys. When it comes to the Zener diode, I want you guys to focus exactly over here. When it comes to the Zener diode, we say it is the diode which is used as a voltage regulator. Like there are different number of Zener diodes in the market out there. Okay, guys, let's suppose I'll bring a Zener diode. This is the symbol of Zener diode. Let's suppose let's suppose voltage is Zener voltage, VZ, it is 10 volts. What does it mean? Means it can, if you connect this parallel to some load, it will maintain the 10 volts of voltage potential difference. Let's suppose we have got another Zener diode. This Zener diode has got 20 volts. So we say this is that Zener diode which will maintain 20 volts. Okay. Okay. Like, if I say, this is the battery, this is the resistance. I'm saying, sir, across this load means this can be television, this can be anything. I'm saying, sir, you should maintain VZ is equal, you should maintain, we say 20 volts of potential difference across this load. If potential difference becomes greater than 20 across the load, it will burn it. So what will you do? You'll buy a Zener diode from the market, which has the Zener voltage of 20. You'll connect parallel to it. Now it will maintain 20 volts across it. If across this it is 20, across this also it will be how much? That is 20. Across this also it will be 20. Okay, so this is how the Zener diode works. This is how the Zener diode works. Like. In the market, there are different Zener diodes available with different fixed voltages. Okay, this has got 20, that has got 10. This can maintain 20 volts across the load, that can maintain 20 volt, 10 volts across the load. Now see, find the current in the Zener diode. See guys, how do you find the current here? This is the voltage, this 100. If I say I current will leave from here, this is current I will flow through here. So can you tell me, okay, one more thing. Guys, what is the voltage across this Zener diode? That is 15. It will maintain 15. Across this also it will be how much? How much will be the voltage? We say V will be 15 volt. Now guys, if this is 15, total is 20. So across this it will be how much? That is 5 volts. Now tell me how much will be the current I. I will be V by R. V is 5 divided by 100. Okay. 5 divided by 100. Now this current I will be divided over here, I Zener. Okay. Okay. And here in this particular case, it will be I resistance. It will be I resistance. Now can I say this current in this particular case, it will be I Zener plus I resistance. Okay, current through the resistance. Now this is 5 divided by 100. And what is this IR? How can you find IR? IR will be voltage, that is 15 divided by 500. 5 threes are 15, 5 100s are. So this is 3 divided by 100. Current in this is 3 by 100. So I is 5 by 100. Okay. Okay, IZ you need to calculate minus 3 divided by 100 will be IZ. So IZ will come out to be 5 minus 3, that is 2 divided by 100. That will be 2 by 100. Now guys, this is the question on Zener diode, which is a good question actually. This was the question which was asked in J Mains 2020. Let me just show you this particular question over here, and that will give you the crystal clear feel of Zener diode. This question is mandatory, much need. See, it is like this. It is like this. You have got input voltage that you are giving in this one. This is the input. Okay. And this is a Zener diode which is connected over here. This is another Zener diode which is connected over here. And then you have got a load resistance. And this will give you the output voltage. This will give you the output voltage. Okay. Yes. This is the output voltage. Now, my dear friends, what I'm trying to say in this particular case is, if you take a look over here, this Zener, this has got 6 volts of Zener voltage. This has got 4 volts, and there is a resistance connected over here, that is 100 ohms. And this resistance RL is 400. You have to find. Guys. We say in this case, let's suppose if you are sending the input voltage of, let's suppose, 1 volts, what will be the output? Always remember, this can maintain how much of voltage? 6. If you send less than 6, it will not work. It remains off. Zener diode doesn't work, it remains off. If you send greater than 6, it will maintain 6 only. Doesn't matter how much you send to it. It will maintain 6 only. Okay. So means when input voltage is 1, this diode remains off because its Zener voltage is 6. This diode also remains off, its Zener voltage is 4. So input is 1, output will be 1. Output will be 1. Okay. When I say input is 2 volts, we say output is 2. Because this is off, this is off. When I say input is 4, we say V output in that case will be 4. Why? This remains off. This will maintain 4 across it. Across this load, across this resistance will be 0. So here output will be 4. If I say V input is 5 volts, what is going to be the V output? Guys, this still remains off. Now see, this will maintain 4 across it. 4 and 1 volt it will give to the resistance. So 4 plus 1 is 5. So output will be 5. If you give V and input as 6 volts, V input as 6 volts. If you give input voltage as 6 volts, now input voltage is 6. This diode gets on, okay, this diode becomes on. It will maintain 6 across it. If across this it is 6, across this it will be 6. Now 4, this diode will take, 2 will go into this resistance. Okay, so output in this particular case will be 6. When you give V input as 7, what will come out to be the V output? So this is 7. It will maintain 6 only. So this will maintain 6 only. So load will be 6 only. So now if you plot the graph, okay, output graph. Guys, we say it will keep on increasing, okay? It will keep on increasing. This is output. So when it was 1 volt, 1 volt, 2 volt, 2 volt, 3 volt, 3 volt. Okay. And when it reaches, we say 6 volt. Okay. And after 6, it becomes constant. Which of the following options? Okay. So we say till 6 it is constant. Then afterwards, sorry, till 6 it is increasing. Then afterwards it is constant. Then afterwards it's constant. Now guys, we have to study Boolean algebra. These logic gates we have to study now. Logic gates we have to study now. Okay. Now we need to start the logic gates, one of the most important topics. Extremely important, guys. My back is paining, guys. Huh? Let's take a break of 10 minutes. So let's take a break of 10 minutes. Break till 12:10 a.m. Now guys, take a look. When it comes to the Boolean algebra, see, in this Boolean algebra, we will be studying different devices. We will be studying different devices in which we will give input, and this device will provide as the output. Now, this input and output is what we call the digital signal. This digital signal will be either in the form of 0 or 1. 0 is also called 0 volts, 1 is also called 5 volts. 0 is also called low, 1 is also called high. 0 is also called off, 1 is also called on. Now guys, let's do the addition of the Boolean algebra. Let's suppose you have 0 plus 0, it is 0. 0 plus 1, it is 1. 1 plus 1, it is 1. Basically, high plus high is always high. Okay? Okay? Here, we say 0 plus 1, high plus low is low. High plus low is high. A plus 0 is A. It is like, sir, what is this A? A can be anything. If I say A plus 0, if we put A as 1, so 1 plus 0 will be 1 plus 0 will be 1. If we put A as 0, so 0 plus 0 will be 0. So answer is coming out to be 1 as well as 0. So means you keep this as A. So A plus 0 is A. A plus 0 is A. Okay, A plus 0 is A. So A plus 1 is 1. A plus A bar is 1. A bar means if I say this is 1, its bar will be 0. If I say this is 0, its 0 bar will be 1. Okay, opposite of 1 is 0, opposite of 0 is 1. A bar means reverse of A. A double bar, these two bars will cancel, it will come out to be A only. Like you have 0 into 0, that is 0. 0 into 1, that is 0. 1 into 1, that is 1. High into high, that is high. A into 0, that is 0. A into 1, that is A. A into A bar, that is 0. Keep all of these things in your mind. Okay. Then you say you have De Morgan's law. What does De Morgan's law say? De Morgan's law says that if you have A plus B whole bar, if you want to break this bar, you can write it over here A bar and then B bar. But this addition sign changes to multiplication. We say this addition sign changes to multiplication. Even if you have something like this, A dot B whole bar, if you want to break this bar, you can write A bar, but this will be plus B bar, A bar plus B bar. Okay, this addition sign changes to this. Now guys, commutative law, it is A plus B is equal to B plus A. Similarly, associative law, what is this? This is A plus B plus C will be equals to A plus B plus C. Okay, here it is A plus B plus C. Here bracket is for A plus B, but here bracket is for B plus C, here bracket is for A plus B. Distributive law, it is A dot B plus C. It is A into B plus A dot C. Now guys, important in this case is gates. There are 3 gates that we need to study: NOT, OR, and we say AND. Then we have 2 universal gates. These are the fundamental gates, 2 universal gates, that is NAND and NOR. Now take a look. NOT gate. It is that gate, guys, which has the job to do the inverse. Let's suppose, and this is the symbol, okay, this one. So we say this is A. Its job is to do the inverse. It will give you the output as A bar. Input is A. It will give you the output as A bar. Now see the truth table. Truth table is the relation between input and output. If you give A, it will give you A bar. If you give 0, it will give you 1. If you give 1, it will give you 0. Just the opposite. Then you see electrical equivalent circuit of NOT gate. Guys, this circuit exactly behaves like NOT gate. This circuit exactly behaves like NOT gate. Let me show you how. Let's make its truth table. See, this is key and this is bulb. This is key, this is bulb. Guys, when you, let's suppose you have connected the battery. When you switch on the key, so current will prefer to flow through this path where there is no resistance. Because bulb has resistance, current will prefer to flow through this path. if current will prefer to flow through this path, so we say when key is on, no current flows through bulb, bulb remains off. Okay, on means 0, off means 1. Okay, and I'll write it like this. This is 1 and this is 0. And when this is on, current cannot flow through this path because it's open. Current has to flow this. When this is sorry, closed, off, the bulb will be on. See, 1001, you can exactly compare it with this one. It is exactly same. We say this circuit behaves like a NOT gate. This circuit behaves like a NOT gate. Okay. This circuit behaves like a NOT gate. Then you have second one, that is OR gate. Take a look, guys. OR gate, this is the symbol of OR gate. This is the symbol of OR gate. The job of OR gate is to do the addition. Okay, the job of OR gate is to do the addition. Keep this thing in your mind. Okay. Now, my dear friends, if the job of OR gate is to do the addition, what is the symbol of OR gate? This is the symbol of OR gate. Okay, something like this. This is the input A, this is the input B, and output will be Y is equal to A plus B. Output will be Y is equal to A plus B. Now, guys, in this particular case, this is the symbol. If you make the truth table, A, B, this is input, this is another input. Output will be, let's suppose A you are giving 0, this is 0. 0 plus 0 is 0. Let's suppose this is 1. 1 plus 0 is 1. 0 plus 1 is 1. 1 plus 1 is 1. 1 plus 1 is 1. Next, this will be electrical equivalent circuit for OR gate. This circuit exactly behaves like OR gate. Let me show you how. See, guys. We say when key 1 is on, okay, and this is off, current can flow through this and bulb remains on. Okay. Let's keep both off. This is off, this is off. Current cannot pass. No current flows through the bulb, bulb remains off. Now, let's keep this as on, this off. Now current will flow through this key, bulb remains on. This is 1, 0, 1. Now we say when this is off, keep this off and keep this on. Current will flow through this path in that particular case, so bulb remains on. When both are on, in that case also bulb is on. So if you compare this truth table with this, it will exactly match. So we say this is the electrical equivalent circuit of OR gate. Then you say AND. When it comes to the AND gate, this is the symbol of AND gate. Okay, this is the symbol of AND gate. And this, the work of this AND gate is to do the multiplication. Y is equal to A dot B. Now, if I say, I'll make a truth table. This is 0, 0. 0 into 0 is 0. 0, 1. 0 into 1 is 0. 1, 0. 1 into 0 is 0. 1, 1. 1 into 1 is 1. 1 into 1 is 1. Okay. Now, this is the electrical equivalent circuit of AND gate. This is the electrical equivalent circuit of AND gate. Then, guys, you have an important gate, that is NOR gate. This gate is important, which is NOR gate. I want you guys to take a look over here. Take a look, guys. When it comes to the NOR gate, nor is simply, guys. It is simply the combination of, we say, not, or we say or plus not, and it will give you nor. Or plus not will give you nor. Now this is OR gate. Its job is to do addition. This is NOT gate. Its job is to do inverse. Let's suppose A and B is the input. This will give you the output of A plus B. Now this A plus B is the input for this NOT gate. It will put the bar. It will do the inverse. So final output will be this. Final output will be this. Okay. And its symbol is directly. Guys, keep this as it is. Instead of this NOT, you put the ball over here. So if A is the input, B is the input, final output is A plus B bar. Final output is A plus B bar. Now truth table. Guys, see. This is A, B. What is the final output? A plus B bar. So 0 plus 0 is 0. Now 0 bar will be 1. 0 plus 1. If this is 0, this is 1. 0 plus 1 is 1. 1 bar is 0. This is the final output. This is 1 plus 0 is 1. 1 bar is 0. 1 plus 1 is 1. 1 bar is 0. 1, 0, 0, 0. Okay. Okay. Now guys, electrical equivalent circuit for NOR gate. So this is that circuit which exactly behaves like a NOR gate. This is that circuit which exactly behaves like a NOR gate. See guys, you have got a battery over here. You have got key 1 over here, okay? You have got key 2 over here. You have got key 2 over here, okay? And this is a bulb, my dear friends. This is a bulb. This is a bulb. Now in this particular case, let's suppose if I say I'll do one thing. I'll keep this off, both are off. We say current will flow through the bulb. There is no other option. Now let's suppose if I do one thing, if I keep this key 1 as on, we say current will prefer this path. Current will prefer this path. Then bulb remains off in that particular case. Okay? Bulb remains off. Now if I say this is on, we say in that case bulb remains off. Okay? So basically, when you match this with this, it exactly matches. So 0, 0, 1, see, on, off. See here, on, off. Now see, on, sorry, this was on, off, on, off, on, off, on, off, on. Now then another one, on, off, on, off, on, off, on, off. Okay. Then you have the next one, that is NAND gate. NAND is simply the combination of, we say, AND plus NOT. NAND is simply the combination of AND plus NOT. Okay? 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 Yes. Now guys, when it comes to the symbol, so this is basically AND, this is NOT. Guys, A and B is the input. This will give you the output of A dot B. Okay? Then it further goes as an input to this. It will give you A dot B bar. So final, we say Boolean expression for NAND gate is Y is equal to A dot B bar. Okay, this is the symbol. This is the symbol. Okay, this will do A dot B and this will basically do the NOT. This is the NOT gate over here. Now guys, truth table, take a look. We say final output for NAND is A dot B bar. So if this is 0, this is 0. 0 into 0 is 0. 0 bar is 1. If this is 0, this is 1. 0 into 1 is 0. 0 bar is 1. If this is 1, this is 0. 1 into 0 is 0. 0 bar is 1. This is 1, this is 1. 1 into 1 is 1. 1 bar is 0. Okay? Okay? This is the truth table. And this is the electrical equivalent circuit. This is the electrical equivalent circuit of NAND gate. If you make the truth table over here, guys, if you make the truth table over here, take a look. You have got K1, you have got K2, and you have got bulb. I'll make it like this only. 0, 0, 1. Let's suppose I'll keep this off, I'll keep this off. So this means 0, this means 0. What about bulb? No current will flow through, no current will flow through this. Bulb will remain on because current has to flow through the bulb. Okay, the second one, 0, 1, 1. Let's say this is off, this is on. Okay, if this is off, current cannot pass over here. Current has to flow through the bulb. Bulb remains on. Next one. 101. Let's check for 101. Now this is on. This is off. Still current cannot flow further. Current has to flow through the bulb. So 10. This will be 1. Now let's keep both on. This is on. This is on. Current will flow through this path. Bulb remains off. 110. 110. Okay. Now, do you see this truth table exactly matches with this truth table? So I can say this circuit exactly behaves like a NAND gate. Now, let's suppose you have a question something like this. Take a look, take a look. So this is plus 6 volt, this is 0 volts over here. Current always flow from higher potential to lower potential. Okay. Current always flow from higher potential to lower potential. Now guys, let's make the truth table over here. Let's make the truth table over here. Okay. So we have got K1, we have got K2, and we have got bulb. Now tell me, guys, let's suppose if we keep K1 off, okay, K1 is off, K2 is also off. So current cannot pass through this, okay, current has to flow through the bulb, bulb remains on. Okay, yes. Let's do one thing, guys. Let's keep K1 on, okay, so current will flow, but here K2 is off. Again, it cannot pass, current has to flow through the bulb, bulb remains off, on. If I keep this as on, off, this as off, sorry, this on, sorry, this off, this on, still bulb remains on because here current cannot cross this, so current has to flow through the bulb. Now, if I keep both on, this is on, this is on, this is on, this is on. Now, current will prefer this particular path. It will not flow through the bulb. Bulb remains off. Now, tell me, which gate is this? This was question asked in Neet 2019. Which gate is this? Okay. 0, 0. Compare the truth table over here. 0, 0, 1, 0, 1, 0, 1, 1, 0. This is NAND gate. This is NAND. Okay, what about this one? I'll recreate this figure. This is 6 volt, this is 0 volt, and that is the bulb. Now guys, see, if you make the truth table in this particular case, this is K1, this is K2, and this is bulb. K1, K2, and this is bulb. K1 and this is K2 and this is bulb. See guys, K1. Let's suppose I'll keep K1 as on, K2 as off. Or let's do one thing. This is on, this is off, this is off. 0, 0. This is off, this is off. So we say in this case, current has to flow through the bulb. Okay, current always flow from higher potential to lower. Current has to flow through the bulb, bulb remains on. If I say this is on, this is off. Key1 is on. If key1 is on, it will flow through the key1 and it will reach over here, bulb remains off. If I say this is off, this is on. Now key 2 is on. It will flow through this, flow through this, flow through this, and bulb remains off. If I say this is on, this is on. Current can flow through this path, current can flow through this path, so bulb remains off. So this is NOR. This is NOR. Yes, it is NOR. Okay. What about this one? In the combination of the following gates, the output Y can be written in terms of the inputs A and B. Can be written in terms of the inputs A and B. Guys, see. This is A. Guys, we have to find the output. This is A. A will directly go over here. This is which gate? This is OR gate. Its job is to do addition. This is OR gate. Okay. If you check this symbol. Sorry, and. This is and that one is OR. This is and. This is and this is OR. Now guys, take a look. We say this is A and this is B over here. Now this is NOT. What is the job of NOT? Its job is to inverse, so it will give B bar. Now this A will go here also, so now it will give A bar. This B will go here also, this is B. This is B. Now guys, this A and B bar will go into the AND. It will multiply A into B bar. Now this A bar into B will go and it will multiply because its job is to multiply A bar into B. Now both of these will go into the OR gate. So final output in this case will come out to be AB bar, then we say plus. This will be A bar B, A bar B. This is the final output. What is, okay, all of these are previous year questions, extremely important. What is the output Y in the following circuit when all the three are first 0 and then 1? See. Put all the three 0. 0, 0, 0. This is AND. Okay. This is NAND. See ball over here. This is NAND. Okay. This will multiply. This will multiply. Okay. So 0 into 0 is 0. Now this 0 will directly go over here. Okay. Now this 0. What is the output of NAND? Y is equal to A dot B bar. This is the output of NAND. Now this 0 into 0 is, first 0 into 0 is 0. So 0 bar will come out to be 1. Okay. So I'll write when all are 0, Y is 1. Now let's do one thing. Let's keep this as 1. This is 1, 1, 1. 1 into 1 is 1. So this 1 will go over here. Now, here in this particular case, Y will be A dot B. 1 into 1 is 1. So 1 bar, it will be 0. So we can say when all are 1, y will be 0. So 1 comma 0 is the answer. With this we have completed this particular chapter also. With this we have completed this particular chapter also. Now guys, okay. Guys, I think rest of the chapters will take in the remain another one shot, okay? We'll take its one more part. I think rest of the chapters will take in that. Will that be okay? Will that be okay? Hmm. Let's complete it in the next part, guys, huh? Because my back is paining extremely. Honestly, I'm speaking. Whatever you say, I'll do that only, okay? You guys say. AC, AC, AC. Chalo, let's start AC. Take a look. Take a look. Direct current. What is a direct current? Before starting alternating current, let's take a look at direct current. We say it is a unidirectional current. It is a unidirectional current. Unidirectional current means which flows only in one direction. Like you have got a battery over here. We say current comes out of the battery and it flows something like this. Current can never come out of the negative terminal. It will come out of the positive terminal only and it will flow something like this. It can never come out of the negative terminal. That is not possible. Okay, so this is the direction of the current from right to left, from positive terminal to negative terminal. I comes out of the positive terminal and goes into the negative terminal. Even if you make its graph, it will be like this from the upper side, okay? Current will be positive only. Positive means direct current, DC, means one directional current only. Okay, if I say what is this? This is AC or DC? Sir, here, in this particular case, current is positive only. Current is positive only. Okay, you see current is positive only. Okay, so means this current has only one direction. This current has only one direction, so it is DC. So it is DC. This is DC, direct current. Now, when it comes to the alternating current, we say it means bidirectional current. It is that current which has two directions. This current can be positive and I can be negative also. It can be positive as well as negative. Guys, like. We say if the graph of the current is like this, you see here current is positive, here current is negative. This is an alternating current, AC. Like this. So here current is positive and then it becomes negative. Then it becomes positive, then it becomes negative. This is called square wave AC. Okay, like. I'll give you the example. This is the alternating source and this is the resistance. So from this alternating source, the current can come out of this side also, this side also. This will be the positive cycle, this will be the negative cycle. So current has two directions. This is a bidirectional current. Okay. When it comes to this, this is called triangular AC. Guys. Or we can say this is sawtooth AC. Sawtooth AC. Okay. This is called sawtooth AC. This is called sawtooth AC. Okay. Now you guys can see over here. This is the sinusoidal AC. This is the sinusoidal AC. So here current is positive and from the lower side current is negative. Means current is changing the direction. This is called square wave AC. This is called square wave AC. Here current from the upper side is positive, from the lower side it is negative. This is not an AC. This is not an AC. Guys. Because here current is positive only. Current does not flow. See, there is no graph is not from the negative side. This is triangular AC. Okay. This is sawtooth AC. This is sawtooth AC. Okay. And this one is not periodic. Okay. Here amplitude is decreasing. Okay. It is not AC. So here amplitude must remain the same, constant. This is sawtooth AC. This is triangular AC. I hope this is crystal and clear. Now, in our syllabus, we have to mostly focus on sinusoidal AC only. Okay. In our syllabus, we have to mostly focus on sinusoidal AC only. Sinusoidal AC will be this AC. Sinusoidal AC will be this AC. Okay. And here, If you ask me what is the equation of the sinusoidal AC, that is going to be this. This will be the equation of sinusoidal AC. This will be the equation of sinusoidal AC. I is equal to I naught. I is equal to I naught sine of omega t plus phi. What is this I naught? This I naught is the maximum current or the peak value. Like, what is the peak value? This is the peak value. That is I naught, amplitude or the maximum value, peak value. I is the instantaneous current. I can be the current at any point. This. Omega is angular frequency. Phi means phase difference. This is phase difference. So we have to mostly study sinusoidal AC only. The equation of sinusoidal AC will look something like this. I naught sine of omega t plus phi. Okay. Now, amplitude. It is the maximum value of the current in the either directions. Okay. Like. We said this is the amplitude, maximum value. This is the amplitude, maximum value. Okay. Okay. Time period, the time taken by the alternating current to complete its one cycle. I'll tell you. See guys, one cycle of an alternating current. Take a look. This will be the one cycle of alternating current. See, here time is 0. Here time is t divided by 4. Here time is, we say, t divided by 2. Here time is 3t divided by 4. Here time is one time period complete. So basically this is called one cycle of alternating current. So how much time it is taking in completing one cycle, that is one time period, that is t. Frequency, it is the number of cycles by an alternating current in one cycle. How many number of cycles, okay, by an alternating current in one cycle? So basically, in one cycle, current changes its direction twice. See. This is one cycle. This is one complete cycle. So how many times current changes direction in one cycle? We say current, this is negative. Okay. So it is changing its direction twice. So in one cycle, it is changing its direction twice. Number of cycles per second means if frequency is 50. If I say frequency is 50, it means number of cycles per second. Means every second it is covering how many cycles? 50. So means if frequency is 50, it will change its direction 100 times in 1 second. It will change its direction 100 times in 1 second. Okay. Yes. Now guys, in an AC, the current is expressed as, this is the current that is given in the AC. This is the current that is given in the AC. So I is equal to 100 sine of 200 pi t. Guys, see, if you have to make its graph would look something like this. Its graph would look something like this. We say in this particular case, in this circuit, current rises from 0 to peak value. This is 0, this is peak. It says that how much time the current is going to take in peak value. You have to find this time. Guys, see. What is the, see, always remember, this is I is equal to I naught. This is the peak value. This is the peak value. This is I naught. This is omega. This is omega and this is t. If you compare it, okay, I is equal to I naught sine omega t. Guys, see. Now, how much time it is going to take till the peak value? So, put this instantaneous current as peak value, 100. And here it is going to be 100 sine of 200 pi t. Okay. If I say how much time it is going to take to reach 50 ampere, so you'll put 50 here. If I say how much time it is going to take in reaching 30 ampere, you'll put 30 here. So you'll be saying, sir, 100, 100. Okay, this and this will cancel. This will be 1. When is the value of 1 for sine? That is sine 90. That is sine of pi divided by 2 will be equals to sine of 200 pi t. Now sine pi. So t 200 into 2 is 1 by 400. So time will come out to be 1 by 400 seconds. So in 1 by 400 seconds, current will reach the peak value. Current will reach the peak value. Okay. Now another one. Take a look at this. The peak value of an alternating current is given by E naught cos omega t. Okay. So peak value of the alternating current E naught is given as 10 volts. Okay. And frequency in this case is given as 50 hertz. Frequency is given as 50 hertz. Time is given as 1 divided by 600 seconds. 1 divided by 600 seconds. The instantaneous value of EMF is, we have to find E. So I can say E in this case will be, that is E naught cos omega t. E naught, that is 10 cos of omega t. How can we write omega? Omega will be 2 pi f into t. Guys, always remember, omega is equal to 2 pi into f also. Omega is equal to 2 pi divided by t also. So you can write E is equal to 10. Then we say cos of 2 pi. What is the value of frequency over here? That is, frequency is given as 50. Time is 1 divided by 600 seconds. This 0, this 0. 5 ones are 5, 12s are. So 2 ones are 2, 6 are. So E will come out to be 10 cos of pi divided by 6. Pi by 6 is cos 30. Okay. Cos 30 is root 3 by 2. So E will come out to be 10. So root 3 divided by 2. 2 ones are 2, 5s are. This will come out to be 5 root 3. This will come out to be 5 root 3. This was the question which was asked in J Mains 2022. The current in the following circuit is given as, this is the current, I is equal to 5 sine of 120 pi t. 5 sine of 120 pi t. How long the current will take to reach the peak value from 0? What is the peak? 5. So put I is equal to 5 over here. Instead of I, you can put I as peak 5. Then I say this will be 5 sine of 120 pi t. 5 and 5 will cancel. So it will be 1. 1, or you write sine of pi by 2. Sine of pi by 2. It will be sine of 120 pi t. Sine will cancel. Pi and pi will cancel. So 120 into 2 is 240. So time will be equals to 1 upon 240 seconds. Okay. Is this clear till over here? Is this clear till over here? Tell me, guys. Just a second, I'll come. Just a second. Now guys, take a look. Average value or mean value. Guys, let's suppose you have discrete quantities x1, x2, x3, x4. You have to find their average. How do you find the average for discrete quantities? You say, sir, x1 plus x2 plus x3 plus x4 divided by 4. This is how you find the average for a discrete quantities. But when it comes to the continuous quantity, how do you find the average? Guys, if I say x is equal to t square, continuous quantity means here, this x1, it will have only one value. X2 will have only one value. X3 will have only one value. But here x has different values. When time t is equal to 1, x is 1. When time t is 2, x is 4. When time t is 3, x is 9. Okay. For continuous quantities, how do we find the average? Guys, directly remember, I have told you many times, integration of, we say x dt upon integration of dt. Like example, if current is flowing I is equal to t, find the average between t is equal to 2 seconds to t is equal to 5 seconds. See? So we have to find the average over here. Average of current. That will be integration of I dt upon integration of dt. So I'll write over here integration of I is given as 2t and this is dt, and we have to find from 2 to 5, so this will be 2 and this will be 5 upon integration of dt from 2 to 5. Now tell me guys, it will be, take this 2 out, integration of t, it is going to be t square divided by 2, and this will be 2 and 5, 2 and 2 will cancel, divided by integration of dt, that is t, and limits are from 2 to 5. Okay. Now this will be 5 square minus 2 square divided by 5 minus 2. This is 25 minus 4 divided by 5 minus 2 is 3. 25 minus 4 is 21 divided by 3. 3 ones are, 3 sevens are. So 7 ampere is the average current over here. Now guys, let's suppose if I ask you, what is the average of sine omega t in the full cycle? Full cycle means, guys, full cycle means from 0 to t. Half cycle means from 0 to t by 2. So it says that you have to find the average of sine omega t. Guys, average of sine omega t in full cycle, how much will be? That is integration of sine omega t dt upon integration of dt, and limits are from 0 to capital T, 0 to capital T. Guys, if you solve this, it will come out to be 0. It will come out to be 0. So we say average of sine omega t in the full cycle, that is 0. Average of cos omega t in the full cycle is 0. Average of sine square omega t in the full cycle is 1 by 2. Cos square omega t is 1 by 2. Sine omega t in the half cycle is 2 by pi. Cos omega t in the half cycle is 2 by pi. Sine square omega t in the half cycle is 1 by 2. Cos square omega t in the half cycle is 1 by 2. You guys are supposed to remember all of these directly. Then we have root mean square value. Root mean square value, that is RMS value, okay? How do you calculate it? Let's suppose you have got a current. You have to find its root mean square value. You take this peak current and divide it with the root 2, it will give you the root mean square value. As simple as that. I naught divided by root 2. If I say I have got current I is equal to 50 sine of 200 pi t. Find its RMS value. You simply say IRMS is going to be peak by root 2. Peak is 50 divided by root 2. In an AC current is expressed as this. Find the time in which current reaches from 0 to peak value. This is homework. I have already shown you the question, something like this. Now guys, if you have a sinusoidal current, guys, if you have sinusoidal current, in this, if you have to find IRMS, you will say I naught by root 2. But if you have a current mixture of AC and DC, guys, here. I is equal to I1, this is DC, plus I2 cos omega t, this is AC. Here, how do you calculate IRMS? That is I1 square plus I2 square divided by 2. Like this is the question. So IRMS, 4 is DC, 5 sin omega t is AC. We'll be saying this is under root of I1 square, that is 4 square plus 5 square divided by 2. Solve it and get the answer. So this formula is valid when alternating current and direct current is given. So basically mixture. And I1 you keep as it is. And alternating current is given by I is equal to I1 cos omega t, I2 cos omega t, plus I2 sin omega t. Find the RMS value of the current. Guys, in this particular case, it is the mixture of two ACs. This is AC, this is also AC. Here, if you have to find the RMS current, that would be simply under root of I1 square plus I2 square divided by 2. Under root of I1 square plus I2 square divided by 2. Directly. Now guys, take a look. This is a sinusoidal AC. In case of sinusoidal AC, I want you guys to remember this directly. We say IRMS will be I naught by root 2. I average in the half cycle is 2 I naught by pi. I average in the half cycle is 2 I naught by pi. Okay. I average in the half cycle is 2 I naught by pi. I average in the full cycle is 0. Guys, if this is a sinusoidal AC, its RMS value is I naught by root 2. Average in half cycle is 2 I naught by pi. Average in full cycle is 0. Now guys, this one is what we call the full wave rectifier. Or we say this is a direct current only. This is a direct current only. Okay. This is positive. In this particular case, if you ever see the current something like this, here IRMS is going to be I naught divided by root 2. And here average current in the half cycle, that is going to be 2 I naught by pi. It will be same. And here I average in the full cycle is going to be 2 I naught by pi. Same. This is called half wave rectifier. Okay. And in this particular case, if they ask you to find the average current, that will be 2 I naught by pi. In the half cycle means from 0 to t by 2. In the full cycle, it will be I naught by pi. In the full cycle, it will be I naught by pi. Okay. IRMS here also in the half cycle. Okay, keep this thing in your mind. IRMS in the half cycle will be I naught by root 2. And IRMS in the full cycle here will be I naught by 2. Keep this thing in your mind. Very important. Square wave AC. For square wave AC, we say average in the full cycle is 0. Average in the full cycle is 0. IRMS will be I naught. IRMS will be I naught only. And this current average in half cycle, that will be I naught only. Average in half cycle will be I naught only. Okay, and average in full cycle is 0. Keep this thing in your mind. This is a triangular AC. For triangular AC, we say average in half cycle is I naught by 2. Okay, average in full cycle is 0. Average in full cycle is 0. In half cycle, it's I naught by 2. And IRMS in this particular case is I naught divided by root 3. I naught divided by root 3. Please don't make the mistake here. I naught divided by root 3. Now let's talk about the phasor diagram. Let's talk about the phasor diagram. Guys, representation of alternating current and voltage by a phasor diagram. See guys. Let's suppose we have different alternating. This is current versus time graph, different alternating currents. This current is starting from 0. Okay. Its equation will be I naught sine omega t. This current is starting from peak. At time t is equal to 0, it is starting from maximum. Its current would be I naught sine omega t plus phi. Here it is plus phi because it is starting from maximum. This current is starting from minimum. Its current would be I naught sine of omega t minus phi because it is starting from minimum minus phi. So these are the different currents over here. Now these are the currents made on the graph. If we have to make these on phasor diagram. In case of a phasor diagram, my dear friends, listen to me very carefully. If we want to make these currents on a phasor diagram, okay, so we represent these currents with an arrow. Okay, and on this axis, if we say this plus axis, we say on this axis, we say we mention what? We say sine omega t. And on this axis, it is minus sine omega t. So from this side, it is cos omega t. It will be minus cos omega t. Okay. So this is the phasor diagram. Now you have to show these currents on this phasor diagram. So we show these currents with the help of a straight line or with an arrow. So this is this one which starts from 0. This will be I naught sine omega t. So I'll make it along I naught sine omega t only. Then you have the next current, which is sine omega t plus phi. If it is plus phi, means what is the difference between this and this? Here it is plus phi angle. Here it is 0. So means it is you have to move in the anti-clockwise. How much? Plus phi. So it would be something like this. It would be something like this. And this is how much? This is phi, plus phi. Okay. And then my dear friends, if I say this would be how much? This is minus phi. This is minus phi. This is plus phi. This is minus phi. This is plus phi. This is minus phi. Okay. And this current in this particular case will be I naught sine of omega t plus phi. Why? Because it leads this current with phi. And here you can write this is I naught sine omega t only. And this would be I naught sine omega t minus phi. Okay. Minus means clockwise, plus means anti-clockwise. Now let's draw these currents on the phasor diagram. Let's draw these currents on the phasor diagram. On this axis, we are mentioning sine omega t. On this axis, we are mentioning cos omega t. This is, sorry. This is minus sine omega t. Okay. This is cos omega t. This is minus cos omega t. Now tell me, this first current, 4 sine omega t plus pi by 6. If it was only pi sine omega t, I would have made along this. But it is sine omega t plus pi by 6. Pi by 6 means 30 degrees. So means sine omega t plus pi by 6. When it comes to the pi by 6, you have to go anti-clockwise. So this would be 30 degrees. Pi by 6 means 30 degrees. Okay. And this is I1. Second one is 5 cos omega t minus pi by 3. If it was only cos omega t, I would have made along this. But it is cos omega t minus pi by 3. Minus pi by 3 means 60 degree. So means clockwise 60 degrees. Minus means clockwise. Plus means anti-clockwise. So if this is 30, so this would be 60. Means it would be on this line only, and it will be a bit longer. Why? Because its amplitude is greater than this one. So this will be I2. This is I2. Then you have to make I3. 4 cos omega t minus pi by 2. Okay. 4 cos omega t minus pi by 2. Pi by 2 means 90. This is cos omega t. Cos omega t minus 90. That will be on this axis. This is I3. Okay. Then you have I4. 3 cos omega t. 3 cos omega t will be on this only. I5 minus 4 sin omega t. So this is plus sin omega t minus 4 sin omega t. This will be I5. I6 4 cos omega t plus pi by 3. 4 cos omega t plus pi. Cos omega t plus pi by 3. This will be I6. I hope this phasor diagram is crystal and clear to each and every single student. You can cross check it here. You can cross check it here. Guys, let's take a break. We'll finish this chapter, then we'll end the session. Okay, guys, now take a look in this particular case. AC source across the pure resistance or pure resistive circuit. Let's suppose you have got a resistance over here, okay? You are connecting this with an AC source. AC source is that source which provides alternating current. This will be its voltage. V is equal to V naught sine omega t. Sir, how does DC source look like? DC source looks like something like this, 20 volts, 30 volts. This is a DC source. So AC source provides alternating current. Okay. And my dear friends, let's suppose current sent by this is I. This is voltage across the resistance, that is VR. Guys, this is directly connected to this. So I can say VR will be equals to V sine omega t only. Now. So V is equal to I into R, I is equal to V divided by R. If we have to find the value of current. So current will be, what is the value of V? V is V sine of omega t. V sine omega t divided by R. This is peak voltage. Peak voltage divided by resistance is peak current. Then you write sine omega t. Now guys, see. This is current, I is equal to I naught sine omega t. This is voltage, V is equal to V naught sine omega t. Okay. Now, if I'm saying, in case of pure resistive circuit, plot the phasor diagram of VR and I. In case of pure resistive circuit, you'll be saying V is equal to V naught sine omega t. I is equal to I naught sine omega t. So V will be something like this. This is V. And this will be I. This will be I. Now in this case, you'll be writing VR and I are in the same phase. Why? Because guys, if you plot this on phasor diagram, we say this is sine omega t. So this will be V and along this only, this will be I. Same direction. So V and I are in the same phase because this is V naught sine omega t, this is I naught sine omega t. Now AC source across pure inductor or pure inductive circuit. That I'll not derive it over here. I'll directly say your voltage is going to be, that is V naught sine omega t. Is it fine now, guys? Come here, take a look. In this case, I'm saying this is AC source across the pure inductor. This is the inductor connected to an AC source. Here voltage is V naught sine omega t, current is minus I naught cos omega t. If you have to plot this on the phasor diagram, it would be something like this. This is minus I naught cos omega t, current. This is voltage V naught sine omega t. Now here, voltage is leading current by pi by 2. Voltage is leading current by pi by 2. So you can make it like this also. Voltage in the upward direction, current in the forward direction. Here, voltage is leading current by pi by 2. Here, voltage is leading current by pi by 2. Here, voltage is leading current by pi by 2. Okay. Then you say AC source across the pure capacitor. AC source across the pure capacitor. Okay. Now, my dear friends, you have got a capacitor over here. You have got a capacitor over here. And we say an alternating source is connected to this pure capacitor. So in this case, we say V is equal to V naught sine omega t. This will be the voltage. Current in this case is I is equal to I naught cos omega t. This is in case of pure capacitor. If you make the phasor diagram, guys, this VC will be along x-axis, okay? like this, V naught sine omega t. Current will be along this because it is I naught cos omega t. Even you can make it like this also. Guys, if you make the current in the forward direction, you have to make VC because VC is lagging current by pi by 2. So make this something like this. VC is lagging current by pi by 2. Okay. So we say here VC lags current by pi by 2. Here V in this VL leads current by pi by 2. Keep this thing in your mind. Then you have series LCR circuit. Guys, take a look. Series LCR means where inductor, capacitor and resistor, all the three are connected to an AC source in series. This is called series LCR circuit. This is called series LCR circuit. Now, if we make the phasor diagram of series LCR circuit, guys, if we make the current in the forward direction, voltage in case of resistance will be also in the same direction. Voltage in case of resistance is also in the same direction. Okay, and we say voltage in case of inductor leads current by pi by 2. And voltage in case of capacitor lags current by pi by 2. Now, if I say, guys, if VL is greater than VC, then this vector is greater than this. So we can write VL minus VC. This will be VR. This will be VNet in that case. So VNet will be under root of VL minus VC whole square plus VR square. Okay, now let's make the impedance diagram. Impedance diagram means where you have to mention the resistances. Take a look, guys. Take a look. I'll make you understand. See. Impedance diagram. Guys, take a look. I can say, let's suppose this is a resistance over here. Its resistance is R. Resistor has resistance R. This is an inductor over here. Always remember, my dear friends, when you have this inductor, it also has resistance. That is called XL. This is the resistance of inductor. This is called capacitive reactance. And you have this capacitor. This capacitor has got the resistance that is called XC. And guys, this XL, remember, it is equal to omega into L. This XC will be equals to 1 divided by omega C. So this is the resistance of inductor. This is the resistance of capacitor. Now you will have to make the phasor diagram. Guys. You will have to make the phasor, you will have to make the impedance diagram. Can I write this? V is equal to I into R? Yes. Can I write this? VL will be equals to current multiplied by its resistance, that is XL. Yes. This will be equals to I into XC. Yes. I you can ignore. So it will be R, XL, XC. So this is called the impedance diagram that is shown over here. That is R, XL, XC. And this will be the current. This is the impedance diagram. Okay. Now in case of this impedance diagram, if I say this XL comes out to be greater than this, if XL is greater than XC, then we can say this will be XL minus XC, this will be R, and this will be the net resistance that is called impedance. So Z is the net resistance of XL minus XC and R and is called impedance. Okay. So basically Z impedance is the net resistance of LCR circuit. So here this is going to be XL minus XC whole square, and even you can find the value of tan phi also. It will be XL minus XC divided by R. XL minus XC divided by R. I hope this is crystalline clear. Now, if LCR is capacitive in nature, guys, in that case, we say XL minus XC, and this will be R, and this will be the net resistance. So Z impedance will be XL minus XC whole square plus R square. This is the value of capacitive reactance and inductive reactance that I told you already. Okay. Let's suppose you have this question. Guys, I'll show you few rest of the things you guys are supposed to calculate. Current in this case is given as 10 sine of 100t. Now peak value from the current is 10 and omega in this case is 100. First and the foremost thing, they are asking us to find the value of XL, XC and Z. How do we find the value of XL? XL is omega into L. Omega is 100 into 0.16. That will be equals to 16 ohms because L is 0.16. XC, 1 upon omega C. 1 upon omega is 100 into C is 500 into 10 raised power minus 6. So this will come out to be 20 ohms. Now here, XC is greater than XL. Check out. If XC is greater than XL, impedance will be XC minus XL whole square plus R square under root of. So we say Z will be equals to under root of XL minus XC whole square plus we say R square. So this will be XL minus XC. What is the value of XL? XL is, see this is XC minus XL. That is 20 minus 16. Its whole square plus R. That is 3 square. And this will be under root of 20 minus 16. 4 square is 16. 16 plus 9 is 25. So this will be root 25 and this will come out to be equals to 5. Z is 5. What is the value of phi? Guys. See, if I make the impedance diagram, this is XL, XC minus XL. This will be R and this will be the net impedance Z and this will be phi. Can you tell me what is the value of tan phi? That is perpendicular by base. That is XC minus XL divided by we say R. Okay. And what is XC minus XL in this particular case? That is 20 minus 16. That is 4. R in this case is R is given as 3. 4 by 3 means phi will be equals to 53 degrees. Because when is the value of tan phi is 4 by 3? When phi is 53 degrees. Okay. Similarly, you can find the value of V naught. V naught will be equals to I naught into Z. Peak voltage into total current. Peak voltage is 10. Z is 5. So this will come out to be that is 50. Okay. Then you will have to make the current equation, voltage equation. Okay. VR of T. I'll show you this one. VR of T. Guys, what is the equation of current? Equation of current is I is equal to 10 sine of 100t. Now voltage and current, voltage in case of resistance and current are in the same phase if you remember. So VR of T, we can write it like this. This will be peak voltage in case of resistance. Okay. Then sine of 100t only because it will be along this same. It will be, we say along the current only. Now this is I into R, sine of 100t. So current in this case is 10. Okay, this is I naught. I naught is the peak. And this is 3. Resistance is 3. Sine of 100t. So this will be 30 sine of 100t. So this is the voltage in case of resistance, that equation. Okay. Now rest of these things you guys are supposed to. Okay. Average power as of now. Ignore this. Power factor means R divided by Z, R by Z. Okay, that is cos phi. Power factor means cos phi, that is R divided by Z, base upon hypotenuse. So this you guys are supposed to do from your end, homework. This also homework, just make the equations. This also homework. Now, if I make the graph between Z and F, impedance and frequency. If I make the graph between Z and F, impedance and frequency in case of LCR circuit, guys, see, Z versus F. Understand this very carefully. This is the value of Z, XL minus XC whole square plus R square. Okay. Okay. XL minus XC whole square plus R square. Now you can say in this particular case, this Z will be, that is under root of omega L minus 1 upon C. What is XL? That is omega into L minus 1 by omega into C whole square plus R square. What is the value of omega? 2 pi into F into L minus 1 upon 2 pi into F into C whole square plus this. Now guys, let's suppose if we keep frequency as 0. So this term will be 0 and 1 divided by 0, this term will be infinity. Infinity square is infinity. Infinity square plus something is infinity. So Z will come out to be infinity. So means when frequency is 0, Z is infinity. That's why it is coming something like this. Second, if you keep XL is equal to XC, if XL is equal to XC, so this term will be cancelled. Now Z will be equals to R. Z will be equals to R square. Root of R square. Square and root will cancel. Z will come out to be R. So at XL is equal to XC, you can directly say value of Z is R. And if you keep frequency as infinity, okay, so this term will become infinite. 1 being infinity, this is 0. This is infinity square is infinity plus something is infinity. So you guys can simply write over here. We say when F is infinity, Z is infinity. So then it would be something like this. So we say F is infinity, Z is infinity. Here, F is 0, Z is infinity. I hope this graph is also clear to you guys. Huh? Resonance condition. Guys, resonance condition is that condition when the value of XC becomes equal to XL. When the value of XC becomes equal to XL, that is called the resonance condition in case of LCR circuit. Okay? Like, value of XC is equal to XL. Omega L is equal to 1 by omega C. Take this omega here. Omega square is 1 by LC. Omega will be equals 1 by under root of LC. This is called resonance angular frequency. Okay. This is called resonance angular frequency. And we say omega is equal to 2 pi f. Instead of omega, you can write 2 pi f 1 divided by under root LC. So now take this 2 pi over here. Frequency will be equals to 1 upon under root of LC. This is called resonant frequency. Previous one was resonant angular frequency. This is called resonant frequency. Okay. Do this from your end because here you have to find the resonance angular frequency. Under root of omega is equal to 1 by under root of LC. Okay. Now, I hope this is clear, guys. This graph is also clear. This is also clear resonance condition. Now you have transformer. Guys. When it comes to a transformer, we say it is a device which is used to step up or step down the alternating voltage. Let's suppose the voltage coming from the outside is large. It needs to step that down. So transformer will do it. If the voltage is coming less, it will increase that voltage. Okay. Simple. When it comes to the transformer, it has got a primary coil over here in which primary current flows IP. This is the input voltage and NP is the number of turns in the primary coil. That's it. This is the secondary coil. Voltage output will be given by the secondary coil. Okay. Supply comes to the transformer. It gives us the output. This is the output current. This is the number of turns in secondary coil. This is the soft iron core. Now see, guys, if we say current flows through the primary coil, okay. So due to that, flux will be created. Directly remember over here. And that flux will be transferred here. This is the flux in secondary coil will be equals to flux in primary coil. Number of turns in secondary, number of turns in primary. This is the formula for flux. And this is the formula for output voltage. Guys, output voltage in case of transformer is input voltage into number of turns in secondary upon number of turns in primary. Okay. Now guys, see. in case of step up transformer. Step up means in which you have to increase the alternating voltage. Let's suppose input voltage is 50. You keep number of turns in the secondary coil twice as number of turns in the primary coil. So output voltage will be input voltage NS by NP. Input is how much? 50. Number of turns in secondary is how much? 2 times number of turns in the primary coil. NP will cancel. 50 into 2 is, we say, 100. So see, voltage has been increased. So how do you increase the voltage in case of step-up transformer? While increasing the number of turns in the secondary coil. Okay. Okay. And when it comes to the step-down transformer, let's suppose input voltage is 100. Number of turns in secondary is 2. Number of turns in primary is 4. So here you decrease the number of turns in secondary. Now see, output voltage is V input NS by NP. You keep this as, this is 100. 2 upon 4. 2 ones are 2 twos are. 2 ones are 2 50s are. Output voltage will come out to be 50. So if you decrease the number of turns in the secondary coil, output voltage will decrease. Okay. And we also define the efficiency of a transformer. Okay. For an ideal transformer, we say efficiency is 100%. And efficiency is simply neta. It is power output divided by power input. Power output divided by power input. The primary winding of a secondary transformer has 500 turns. So NP is 500. Its secondary has 5000 turns. NS is 5000. The primary is connected to an AC supply of 20 volts. Okay, V input is given as 20 volts. The secondary will have an output of, we are supposed to find V output. V output will be simply V input, number of turns in secondary upon number of turns in primary. So that is 50, and this will be 500 divided by 5020. This. 5 ones are 5, 10s are. 10 ones are 10. Okay, I made a mistake. Number of turns in primary. So this is 20. Number of turns in secondary is 5000. Divided by number of turns in primary is 500. This and this will cancel. 5 ones are 5, 10s are. Now this 10 into 20. So this will be 200 volts. Okay. So guys, that is all for today. We are done with this chapter also. Thank you. I would want you guys to let me know in the chats how was the session, okay? Rest of the chapters will be completing in one more part. Okay, is that clear? Do let me know how was the session once I end the live stream. Okay. Hello guys, take care. Bye bye. See you guys very soon. Thank you.